So, good morning, good afternoon, and I believe it's actually good evening to some of our international attendees. Welcome to day 2 of our open source science for ESO mission processing study workshop. So we had a very successful and shall I say interactive day 1 yesterday. So I want to thank everyone for their feedback, their comments, their questions, their responses. This is exactly what we were looking for. And we couldn't be happier. The software architecture working group was able to get a lot of questions answered, as well as the community. There was a lot of valuable discussion on open source science, including determining the correct boundaries between openness and IT security. I know this is a question that always comes up. We are not trying to skirt any IT security rules, but we are trying to push forward and be as open as possible. And there is a line there, and we're very cognizant of that. Thanks to hats off to Nancy for making sure we did recognize that we need to enable applications as well as Earth system science. And we will be following up with you to make sure we have a strong alliance and are meeting the requirements on that side. We also got some good reminders that there are a lot of lessons learned from the early days of the OS that can benefit the study. So I know there's some past documentation that has already been circulated to the architecture working group, and we will be looking out for more of that to be sent. So we have a full agenda today. We're going to hear from the ESO core missions to help actually ground us in reality of the scope that we're trying to achieve during this about 12-month study that we're undertaking. But before we begin, I just wanted to give some housekeeping reminders that I gave yesterday. So again, the workshop is being recorded. All the proceedings from the workshop, including the notes, responses to the questions that were asked, will all be posted on the workshop's website. We'll put that again in the chat window. We are asking that you include your full name, first and last, in your display name, not your initials or nicknames. This helps us recognize you if we're going to call on you to ask one of your questions and if you're having any issues. And if you do experience any technical issues, we do have technicians standing by. Their name says tech, T-E-C-H, or it may say tech and then their name. And you can actually send them a chat message privately and they will help you there. A little bit different than today. I know we had some little bit of hiccups or issues unmuting and muting people today. Don't run with this power, but everyone has the ability to unmute yourself. However, we can mute everyone. So we ask that you please make sure you are muted if you're not speaking. Our tech staff will be looking out for any open mics. So please be aware of that. So our workshop MC for today will be Sarah Lupkin. Sarah will be keeping us on schedule as Karen did a great job yesterday. So don't take it personal if she interrupts any of us to tell us that we only have a couple minutes left in our session. There is a dedicated question and answer period after each session, but you can ask questions throughout the presentations and just provide them in the chat window. And similar to yesterday, we are prioritizing the questions to the study architecture working group. And if we don't get a chance to answer any particular questions, we're keeping a log of these and they will be answered later. So our session today will be, the first session is being kicked off with the NISAR mission. And our first speaker is NASA program scientist Gerald Baldwin. Before Gerald begins, are there any questions or anything that anyone wants to bring up before we start? I'll look for also hand raises. That was also a good option we used yesterday. You do have the option to raise your hand with the WebEx technology.
Okay. Ready?
Over to you, Gerald. Thanks.
Okay. Thank you. Hopefully my sound's coming through. Am I audible?
Yes, everything sounds great.
Um, I've got the distinction to go ahead and kick off I guess, the DO as well as NISAR summaries. And so I do want to make sure everybody understands we got NISAR is going to be the first mission out of the gate of ESO with SDC, surface deformation change, is at the back end. And so will these missions look identical or not? That's to be determined because the study is underway, but their capabilities, there's significant overlaps with them. So from our perspective, what's applying for NISAR will also apply for SDC. So next slide, please. So I'm first going to go ahead and start off with talking a little bit about what NISAR is. I'm not going to go down into the weeds with it, but NISAR is really, I'm not going to use the term flagship mission, but yeah, I am. What NISAR is going to do is we're looking at I'll say the climate with basically with the ice sheets, glacier motion. We've got the whole ecosystems, everything from biomass to disturbance, the solid earth with earthquakes, volcanoes, landslides, subsidence with it. We are looking at the whole Earth, basically on every orbit. And so you can see we've got a number of also applications to go with it from hydrology, surface water extent, carbon sequestration, enhancing agriculture. We've got a whole agriculture piece to NISAR. I encourage everybody to take a look at NISAR, and I'll go ahead and I'll either post it or somebody else will. Go to the NISAR website, which is nisar.jpl.nasa.gov. You can really see all the amazing science that we're doing with it, including we've got 26 white papers on applications. So something that NISAR has actually done a really good job with reaching out to our applied science community. So next slide, please. What NISAR is producing is a lot of different types of imagery and capabilities. So the fundamentals of radar, you've got two different pieces that we work with. One's called the SAR backscatter. It's a radar reflective properties of the land surface. And from that, you're able to produce some of the images in the upper right-hand corner of the quad chart with basically the ecosystem, biomass calculations, surface water hydrology, and then the geodetic imaging piece, which is the phase. So this is the left half of the image where you got the interferograms showing deformation from the ridge-curved earthquake, I think inflation or deflation in Hawaii, landslide motion, land subsidence due to groundwater pumping. The lower corner on the left shows what we're doing with ice sheets and glaciers. So you're actually able to measure at the sub-centimeter level motion from space. And so this is what NISAR is going to enable us to be able to do. And then when we fold it into other sciences like hydrology, land cover, land use change, hazard response, there's just so much that we're going to be able to do with NISAR. Next slide, please. So the challenges with NISAR are that we are actually covering all land, all ice on every orbit. This means we've got a lot of data that's coming in. All of our research basically spans all the focus areas and all the applied science program areas as well. The volume of NISAR, say it's staggering. This is actually, if this is actually out online, we could actually click on it. The 2017 is actually a link to a publication that came out that identified that if we take a look at the amount of data that NISAR is anticipated to collect this was done in 2017, we look at all of the ESDIS archive at the time, we had 22 petabytes. Within the 3-year lifespan of NISAR, we're anticipating about 140 petabytes. So in 3 years, we've got a 6-fold increase to ESDIS holdings. Everything has changed. We got more things in there now, so I don't know how these numbers would shake out. But at the end of the day, we've got huge volumes of data. And so it's going to represent some changes in how we need to work with the data to address our specific science. So next slide, please. So there were a number of questions that were actually proposed by the study team, and the rest of the presentation is kind of going through and working with many of these. So it was basically, okay, what's the scope and responsibility of the program objectives for NISAR? And I'm putting my response in the context of basically this workshop, because the overall scope and responsibility of NISAR is much larger than what we're looking at here. But at the top, I want to ensure that basically the NISAR data are used to its fullest potential. Craig Dobson, my predecessor, a program scientist for NISAR, he says he wanted to make sure that no photon was unused from NISAR. And I fully adapted and embraced that concept. We need to make sure that the data are used and available. So to do this, we basically have to lower the bar for usability with the NISAR data and its products. So NISAR data, radar data is complex. And what I mean by complex, remember back to uh, complex numbers, we have a real and imaginary part. The real part of the data is basically the SAR backscatter. So these are the grayscale images to tell us what's on the ground. And then the imaginary part is the phase. It's a sine wavelength of what comes back from the ground. And this is how we're able to measure the land surface deformation. Almost very few people know how to work with complex data. And so how do we take the SAR out of SAR to make it accessible and usable to the broader area? What NISAR's doing, and Paul's going to cover this, Paul and Bud Cook will cover this in greater detail. We're going to, for the backscatter, we're going to generate radiometric terrain corrected products that we actually remove all these different pieces from the radar imagery and turn it into a grayscale image that's really the radar reflective properties of the land surface, such that then you can go ahead and compare it directly with, say, a Landsat or MODIS or any other data set. The other thing we're doing is working on generating interferograms. My first interferogram took me over 2 days to generate. Now what we're going to do is we don't, the end user doesn't need specialized software. They can actually go to the to ASF and download whatever interferograms that they desire from it. So we are taking as much as we can the SAR out of SAR such that we have these products such that the broader audience could go ahead and take advantage of it. Why is this different from other missions? NISAR is going to be the first mission out there with free and open data policy where we're actually generating these level 2 products, as well as level 3 for global soil moisture things the satellite needs working group. So instead of actually having to download the complex data, analyze it with special software to get it into a product that you need and then do your analysis, NISAR upfront is doing this. So that's going to be a major step forward with being able to go ahead and work on our goals of being able to expand and grow the SAR community, because we've actually made it a lot easier for access. So far, we've done a number of things, including having an applications workshop. So far, we've had 10 applied science-based workshops, and we've got 2 in the works for next year. We're also having our first science workshop next April, first one since 2004. So we are working to go ahead and expand the usership, and it's basically through the fact that we have these higher level products. So I see that open source science will really help us to develop the tools and grow these communities. So I actually see the thesis of what we're working on in this workshop is to basically help grow the community. And I think it's essential for NISAR. Next slide. So how does open science fit within your program objectives? For me, it's simply the pathway forward with NISAR is the ability to go ahead and move beyond the level 2 and begin developing level 3 and level 4 products. This could be done with cloud computing and also I think with open source science. NISAR is going to systematically, since NISAR is systematically collecting L-band SAR data, it's going to be a paradigm shift for the sciences as well as applications. For our science right now, that tends to be a lot more, I'll say, local and regional in scope. We're going to be able to start looking at more continental scale as well as global science questions, depending on what your science objectives are. We're going to be moving from a world of just data characterization. Here's an interferogram. We're able to go ahead and describe here's how much moved in an earthquake, to starting to really look at much larger processes that integrate multiple data sources. So we ultimately start understanding the fundamental geophysics that are driving whatever the targeted process is. And the other part with open system science is basically how do we how do we best take advantage of the large volume of data that NISAR is going to produce? And I really see that open source science will help with that. Another question that was on the list is what investments are you making towards open science and what are your expected outcomes? For NISAR, we're doing our ATBDs and Jupyter notebooks, so that way anybody that wants to go ahead and execute some of the same codes that we're doing, they have access to it. Through Kevin Murphy, we had the Griffin project getting ready for NISAR. That was kind of a trailblazer with how do we work in moving into the cloud, what's needed for large scale processing. So Griffin was an excellent beginning precursor to where we're moving towards today. Alaska Satellite Facilities got their Open SAR Lab, which is, I'll say, kind of a sandbox for learning how to work in the cloud and being able to go ahead and work towards working with a radar data in the cloud. So to me, that those are some of the good first steps. But I think that the results from this workshop will be able to go ahead and take these much further. The next couple presentations by both Paul and Hope will likely go into these in more detail than I have done here. Next slide, please. What barriers exist? You've got several different pieces here. We need easy pathways, incentive for bringing researchers, both new and established, into the cloud. I kind of have the tongue in cheek off the side. It's hard to teach old dogs new tricks. Um, there are so many PIs that basically have existing algorithms. They've got their systems that are set up, and working with basically moving into cloud computing, then ultimately open source science. They need to have some sort of incentive. Why should they migrate to the cloud? What type of encouraging system is needed to go ahead and do this? I've been told by a number of PIs that universities actually have their own cloud platforms. They set them up. So what that means is basically when PIs propose, they in the ROSA solicitation, it actually or in their budget, it has a line for the local processing versus cloud computing. So that means they're working locally and they're not working and being able to collaborate with on a larger scale. So we've got some of these things like this that we've got to work through. Um, to address kind of the scale, this issue, again, the old dog new trick type mentality, radar data has been out for a couple decades now. So NISAR, for my vision of the NISAR early adopter, was less how to teach people how to process radar data, because again, it's been out there for a while, but it was actually trying to move people into the cloud. And so then from the cloud, the next logical step is open source science. And so I have a pretty strong opinion that I actually think that every mission should actually have an open science, cloud computing early adopters piece. So basically teaches the community, both the new dogs as well as the old dogs, so the puppies and the well-established dogs, and basically what does it mean to work in the cloud and to be able to move from there. I know I keep on mentioning the cloud and we've got open source science. In my mind, open source science resides in the cloud. And so if somebody's not working in the cloud, they're not going to be as open, or they're not going to be as uh, able to go ahead and participate in open source science. So I think, so in my mind, when I'm describing these things, when I'm talking about cloud computing, that is the pathway. It's the enabler for open source science. Again, it's how I think of it. Other people may have other minds here, but in how I'm describing this is my mindset. With NISAR, we actually kind of proposed an idea for a cloud computing early adopter program that was not well received. So we actually took it back to kind of more old school with the early adopter, but I think we missed an opportunity to work on reaching out to the existing community and to help encourage them to move into the cloud. In the cloud and then open source processing. I feel that a successful OSS program will have a cloud entry point that is very compelling for researchers to make the transition. It provides tools and capabilities they may not have access to. So again, why do you make the transition? Why do you go through the pain? And so there has to be some extra carrots there to go ahead and bring them in. And then from that, the ability to go ahead and encourage them to go ahead and develop new tools, new algorithms. So why it is in their best interest? What do they have to gain? Next slide. What barriers exist across NASA that inhibit participation for open science? So this part, continue this. We need to provide a mechanism to track success and thereby help incentivize the process. Most PIs are publish or perish. So this is either academic or with US government research grade employees. You get graded on your publications. And so a open source tool does not equate with a publication. And so a 4-page publication versus a 10,000 line code, what's going to get somebody advanced? A 4-page publication. So we've got to work on coming up with some way to go ahead and some mechanism to provide success and be able to go ahead and make it such that the community's interested in going to open source science. My screen for a second. Access. The open source science tools need to be well integrated with data access. That leads into discoverability, quality control. Why is one approach better than another approach? the kind of Apple Store type way, and some sort of reward system. Do we have carrots or sticks? I'm not a fan of carrots, of sticks, so I want basically more carrots out there on the positive side to get people in. Next slide. Vision for mission data processing. What does it mean for the mission data processing support open science? For me, basically efficient algorithms. Oh, sorry, I got ahead of myself with that. The algorithms necessary for NISAR are basically open from, I'll say, level 1 and beyond. This includes all the level 2 products and science CalVal algorithms and level 3 products if they're available. And again, for us, what we're doing with NISARs, our ATBDs are in Jupyter Notebooks, so that provides that easy access up front. What does it mean for a mission data processing system to enable Earth science? To me, it means basically the products need to be in a format that is widely accessible to the target communities, not only within radar, the missions, but also cross missions. So you're able to go ahead and bring in data from, say, Landsat and Sentinel-2s in with the Sentinel-1s and NISAR. So if we want to be able to enable our science, all the data has to be in a format and a system that is basically easy to do this type of science. So ARDs are clearly the way to go with this. Read down. One item I want to point out at the bottom is what NISAR is doing for actually working kind of in the international piece, at least coordinating with different SARs, is Bruce Chapman is the NISAR CalVal lead, and he's also the co-chair of CS Committee Working Group on CalVal for SAR. So we are having high-level people within COS that are able to help guide, make sure that NISAR is embedded with that, but also the other agencies know what's going on with NISAR, so that we have more of an open process. Next slide. Okay, what does it mean for the mission data processing system to be efficient? If we're not processing data from the sheer volume of data that NISAR is producing, there's going to be a backlog. So we need to have a very efficient system. And for the next question, the next presentations, we'll go ahead and dive deeper into it. So I think last slide, guidance for the study. The vision for ESO is to study the Earth as an interconnected system with a co-collection of measurements from the DO constellations plus NISAR. Therefore, all of these measurements that we're collecting must be easy to combine and co-analyze. So we take it from the measurements to the modeling to the scientific understanding, and all start with having data that can be combined. So the MDPS is the starting point for this, hence the workshop. We need to understand the source of the data for each of the ESO missions and when to transform it into products. What products make the most sense to be able to be combined that it's also the biggest bang on the investment. We need to understand that the data products, how they can actually be worked and integrated into some of these larger questions. So I've got 4 different, looking at each of the different DO studies and NISAR for looking at, say, food security type questions. And what can each of them do? To actually work with, say, food security with this particular question, we need all this data to be able to be worked together and in harmony such that we're able to do it. We need to incentivize a culture for open source science and cloud computing. If it's too much work to actually do this, or no apparent benefit to our end users, then they're not going to take it on, and therefore it's not going to be successful. So the incentives have to be true and real. Satellite needs working group activities that are out there. They must be included within this. There's a lot of work that's going on. They are lowering the bar for a lot of the different products that should be integrated into this overall architecture and structure. Even though these are not DO missions, they're acting like DO type capabilities, so they should be integrated. And I'm going to say start now, and with NISAR. You've got NISAR at the beginning, SDC at the tail end, and we've got this vast amount of data from NISAR and then ultimately SDC. There are going to be huge challenges to work with, but yet if we take a look at what SDC and NISAR are providing with our data, spanning almost all the focus area sciences, I think it's a good backbone for the overall study and the overall success of this activity. So with that, it looks like I'm ending on time.
You are right on time. Thanks, Gerald. Paul, you're next.
All right.
let's get started. Gerald, as usual, since we talk regularly every week, covered quite a bit of the material that's in this package. This goes down a slightly lower level, so we'll go through it, and I'll try not to emphasize things that are already stated. So next slide, please. All right, for the mission objectives and level 1 requirements, questions that were posed, I decided to put a table in here just to summarize the many aspects of the data problem for NISAR that Gerald started with. We do have a very high data rate with a custom 4 gigabit per second downlink that was developed for NISAR, which leads to a rather large raw data volume, petabytes over a 3-year mission, and at least 100 petabytes over the 3-year mission of the higher level products. We have latency requirements in the PLRA that are much more relaxed than what you see here, but we're shooting for, in this production system, 1 to 2 day latency once we get a reasonable quality orbit from the orbit reconstruction people. And we have a dedicated urgent response mechanism within the program to get data for certain urgent events out within 5 hours. And that's actually to level 0 data, but then the processing system can deliver products to higher level shortly thereafter. As Gerald mentioned, we have products that are global to level 0 and level 2, and those are listed on the right there. You can see we have raw data. We have these so-called single look complex images, which is our complex amplitude and phase images of every spot on the ground. We form nearest neighbor interferograms from that also, and those level 1 products are in radar coordinates. The level 2 products are versions of those geocoded. So we actually, for the first time of any mission, have a single look complex geocoded product, which we believe will revolutionize the use of these geocoded data. We know people like Google are trying to get these kinds of products into their Google Earth Engine system, as well as some derived products that are geolocated. The single look complex data represent the largest volume of processed data. Unlike many other missions, we're processing data at higher levels only at our validation sites. There's a number of reasons for this. It was a big back and forth with NASA back 10 years ago. But these products are listed on the right: global deformation, ground deformation time series, ice sheet velocity time series, sea ice deformation, and various ecosystems targets, biomass, annual and seasonal, disturbance time series, wetlands and agriculture area. So these are all open source algorithms right now, and we expect to be able to give the software and the data to users of this in a cloud environment and allow them to produce their own higher level products or validate what we did with our validation. Next slide. Okay, so this was also part of the request for the level 1 requirement. So our plan for algorithm development analysis in CalVal is stated here. A lot of words on all these charts, so I'm going to try to not read them. We have an algorithmic development team. They develop the level 0, level 2 product algorithms in an open source environment. These have already been open sourced for us. The science team develops the higher level product algorithms, also an open source environment. We consult with the ADT with those things. And we also develop our validation workflows in an open source environment. All of these things will be available to the community to sort of co-develop and check on what we're doing. It's all going to be through this cloud-based system that Gerald mentioned, and we expect our partners, both on the U.S. science team outside of the project and CalVal partners, to have access to this system throughout the development cycle and the operation cycle. Right now, it's behind a firewall at JPL, which is a really large limiting factor. And I guess, as Andy said at the beginning, this must have been discussed yesterday when I couldn't attend, but this is a big stumbling block for the openness of the system. We do have a partner in ISRO. They are not currently fully integrated with us for a variety of reasons that I can't go into. We don't really plan to have a common production platform with them, but we will be sharing data through common portals. And then the plan for groups to collaborate is through the GitHub, GitLab, and mirrored CalVal sites for the software, as I mentioned. And we have been working very carefully with ASF, who has developed some very nice tools for cloud access to data and processing, such as their OpenSAR lab and Hype system. So we expect that to grow in the future. Next slide. Okay, this is very dense, so I'll try not to read it again. So for how will level 1 plus products be generated? So you can read the details. We have specific algorithms. These are all available on the web now through the GitLab at level 1 and level 2. So the level 0 to 2 are project generated. The level 3 are science team derived, but only at the validation sites, as I mentioned. The resources needed are AWS. We use pretty standard toolboxes for coding, C++, and Python, as well as a bunch of open source packages in Conda environments. And the data will be at the ASF DAC, which is also in AWS. So it's a little bit like just flipping a switch to go from the production system to the archive. Hook, I'm sure, will have more to say about that after me. Portability is an issue. We have all of these workflows are open sourced, and we have them developed in Conda environments, which tend to be reasonably portable, actually. But if you try to build these software in other environments, particularly the package compatibility can be an issue at times. I have struggled mightily myself porting the software to my laptop and other platforms. So this is something I think could be done better within the project, overall portability, but we do have a process for configuration management through Conda environments at the moment. The ways that we support system science, you can see them listed there. I'm not going to read them, but basically we use these data to constrain models of various sorts. As Gerald mentioned, right now we tend to focus on local processes, but we're starting with the availability of large volumes of Sentinel-1 data, which is a C-band version of what NISAR will do with slightly less coverage. We're starting to see, continental scale or at least subcontinental scale modeling efforts beginning. But NISAR will change that through its persistence and data quality to really allow very large scale problems to be looked at. And the pain points, as Gerald mentioned, it's the cloud computing environment. We don't really have all the tools in place for cloud computing. I know NASA has invested some in this area, such as the MAP project, but we are just scratching the surface there. I talk to community members all the time who are still not convinced that it's cheaper to go on the cloud for them. So we need to work on that. Gerald mentioned that. And at the moment, we are not tackling the biggest problems because of data availability issues and the cost of processing large data sets. So I don't think we fully understand the scope of what we're going to be ending up doing with NISAR data. So these are pain points. Next chart. So yes, consider the data products open access. Thinking about it, at what point you consider them open access. In my opinion, there should be no period of exclusivity. As soon as the data are out there, they are marked as whatever level quality they are and given to the community. I don't know that everybody agrees with this philosophy, but that's been my approach with data. Radar data tends to be kind of noisy and has issues, understandability issues anyway, so holding on to it, I don't think does anybody any good. We should just get it out there, get the community working on it. As Gerald mentioned, we have a lot of interaction with the outside community. Gerald's work with the Satellite Need Working Group has really made a difference in the usability of these data. We've also had, as you mentioned, many workshops to try to socialize the data and the value of those data. For science, I think measures programs at NASA, NSF partnerships will help grow the products at higher levels beyond the level 2 global products. Authenticating a user right now, we accept software in our open source environment through a contributed area. Generally speaking, there's pretty healthy interaction with the community through the various communication tools that are provided with GitHub. And people, when we see something that's good on the project team, we tend to look at that and test it. And if it gets vetted properly, then we can put it into the project area. So we do have a process. It's a little informal at the moment because not that many people contribute to it. But historical developments have been quite successful in this regard, I'd say. We have a previous version of our software that was done in this way and was very, very active, and we had a lot of innovations through community input. Right now, what we're doing is we have a validation process for our science requirements to validate that we have the science requirements. So we have test sites, we have ground truth data, we run our algorithms, and we see that they're validated. Any new algorithms that community would want to contribute, we would require them to go through the same process. In terms of the project support for open science through documentation, of course, the project will fully support the software that we put out on GitHub through the development cycle and the operations of the project. Of course, the project won't last forever. So I believe that there is a need for dedicated funding for this kind of maintenance after the project sunsets. Maybe that's done through the DAX, maybe it's done through a dedicated maintenance program in Estes. That's perhaps something that will come out of this workshop. And we have our algorithms and validation workflows in these Jupyter notebooks, and the documentation and code are intertwined in those notebooks. So assuming we do a good job at putting those together, which is my goal as project scientist, we will have the good documentation and a platform for the community to springboard off of. So far, we've used Jupyter notebooks for about 5 years now, and they are really, really great for this kind of thing.
2 minutes.
How much time do I have?
That was your 2-minute warning.
2 minutes. Okay. Well, how could a common framework amplify the project science objectives? I think that's a little bit of motherhood. I don't really know the direct answer, but you can read those slides. One thing that I am very keen on is visualization of algorithmic workflows and data products. I think the tools in that area tend to be terrible, and we don't put enough emphasis on it because we think it's an engineering problem. So that's something that I think we should do. Okay, next slide. Yeah, so security is a big issue for constraints on making progress. I think there's a lot of things that could be done that I've kind of mentioned: cloud tool development. I think machine learning assisted workflow management, where you collect metrics on processing and use that to help you guide future processing. Something is not done very much. And then the software maintenance issues that I mentioned earlier, I think are important for the long term. Next slide.
Slide.
Oh, that's it? Okay. Wow. Excellent. So on to Hook, I guess.
Thanks so much. Hook, you're up.
All right, I'll be presenting about the data processing system perspective. This is actually the culmination of all of the hard work from the science data system team. For the NISAR mission, the algorithm development team that Gerald and Paul mentioned are actually part of the science data system team organization here. So it would include a lot of the efforts done by the algorithm development team here. Next slide. Okay, so this is actually the big picture view of the composition of the science data system team. It includes many of the obligatory functional capabilities, such as receiving or ingesting data from the ground link stations. Mainly from the ground data system, which includes a lot of the raw data coming in from the ground link stations, as well as generating the products. And as Paul noted, for the NISAR case, the standard product go up to level 2, but for the CalVal case, it includes some level 3 products for the CalVal sites. But for the NISAR case, it actually includes high priority processing with respect to some of the urgent response capabilities. And then more recently, a lot of effort has been put to also add in the requirements to support the algorithm development done by the algorithm development team, CalVal, and the science team needs. This is mainly in the context of on-demand processing, but how we would describe on-demand processing is actually quite similar to and analogous to a lot of these capabilities are being discussed in terms of an open science platform for algorithm development. It's exactly in the long lines of what Paul just mentioned about having Jupyter notebooks as the basis of the environment, and how do we connect that into the canonical science data system and bridge the two worlds together. So mainly so that the science team has access to taking their algorithms and being able to deploy it and run in the same system that the standard products are used to be generated. If you look at the overall view though, on the left end is mainly the GDS, on the right end is the ASF DAX. For the NISAR case, all of the ground data systems, the science data systems, and the ASF DAC are actually all co-located in the Amazon Oregon region. So this is great in terms of helping to mitigate a lot of the data migration issues, as well as cost as well. Also unique to NISAR is the fact that, as Paul mentioned, it is both composed of an L-SAR, L-band SAR instrument, as well as an S-band SAR instrument. So there is actually data exchange with the Israel Science Data System as well. And then on the bottom there, you can see all of the access from many of the different user types that we mentioned. I think we can go on to the next slide here. So here, this is an overall component view of what the functional capabilities of the science data system scope is. It actually started off as some of the key science data processing requirements in terms of getting data external to the science data system, which here in this case on the lower right would include the ground data systems that we just talked about, and other data providers, say for some of the ancillary data like external DEMs and the like. But all of that data gets ingested into an internal data store used by the science data system in the cloud, and then the science data system uses those to generate products. But for the on-demand use cases, for supporting like the algorithm development and CalVal and science team needs, the science data system team has been working on an on-demand environment. That's kind of like that upper middle portion there for the algorithm development environment, where the idea is, can we have a hosted Jupyter environment that allows users to log in and edit and develop their algorithms in a Jupyter notebook context, but take the same notebooks and build them into containerized and reproducible units that are then registered into the same science data processing services to execute. So the idea is to bridge the gap where on one end you have algorithm developers, on the other end are science data processing, the scalable data processing services, and how do we connect the two together so that the algorithm development use cases actually have access to the large scaling power of the science data processing system, basically. And so in a sense, this gives us this full round trip where algorithms are developed, deployed into the science data processing for not just doing standard products, but also for doing CalVal and science analysis, as well as generating data that is then accessed back from the notebooks for the analysis themselves. On the next slide is another view. Sorry, this was actually originally animated, but now we're just seeing the culmination of all the animation. It looks like a mess, but I'll just hit the highlights. Mainly, it was just to give a sense of what are the key components of the infrastructure. The main themes here is that it's all in the cloud. it utilizes the scalability of two key things. One is the scalable capabilities provided by cloud vendors such as Amazon, where the storage is highly scalable, as well as the compute is highly scalable. And the overall theme is that every single compute and storage is auto-scaled as needed. So meaning that as data gets ingested in, the system automatically scales up compute workers to crunch through the whole extract, transform, load steps, and then the workflows run to actually process from level 0 to level 2 for the standard product production. And then finally, there are also auto-scaling units that would deliver these products to the ASF jack through the cloud notification mechanism. Next slide, please. This is one of the requested slides in terms of what is the implementation plan schedule, mainly to get a sense of what were the key things done from about the MCR timeframe to the science phase. We had to dig through some of the older calendars to kind of get to show the key items of interest and in and around after MCR, the early phase A to phase B to phase C. But effectively, there were some key things that the science data system team had to work on. You can kind of see there on the left-hand side there around the 2017, 2018, 2019 timeframe. Early on, it was recognized that perhaps GPUs may be of use in terms of accelerating some of the large-scale processing needs. This is a lot of the activities that the algorithm development team conducted, and you kind of see that part of the roadmap road towards CDR was a lot of these assessments and reviews, lots of reviews, whether it's a design peer review or a line peer review, as well as other activities, which included cost reviews with Amazon, as well as I think Gerald mentioned about the getting ready for NISAR, the Griffin. A lot of the lessons learned were fed into some of the early design phases for NISAR. As well as now you can kind of see towards the implementation phases, like in phase C and D, there are a lot of activities being done in terms of the development of the algorithm steps, the PGEs as the missions call it, the workflows, as well as integrating it into the actual processing service system. Last note here is on the bottom right. We're asked to note what are some inherited software capabilities. I think aside from the Jupyter notebooks that Paul mentioned, GDAL is used, NumPy is used, but in terms of NASA-funded software that has been open source by the algorithm development team, the ICE software has been heavily used and is still being used, version 2 and then now version 3, as the key science algorithm software for generating the science data products. On the science data system side, there's another open source project used, HiSDS, used for driving the core science data processing capabilities. Both of these projects are NASA funded, but they're also been migrated into the open source. And exactly to Paul's point, they are now being developed in the public, in the open, as well as these projects contributing back to these open source projects during development. Next slide, please. So in terms of some of these key aspects to support the Earth system science, one of the key questions that we were asked was, does the system actually use or share these type of artifacts? And I think definitely NISAR science data systems includes a variety of things, right? It's not just the algorithms and the data, it's the IT security plans, the processes, procedures, workflows, even the expertise, right? It's the workforce itself that understands these things. A lot of these artifacts are actually shared across different projects. Specifically, it's some of these assets are actually shared, and know-how and software is shared with SWAT, SMAP, more recently OPERA, the SNWG OPERA project, as well as MAP. And even more interestingly, the NISAR products will actually be used by the SNWG OPERA project, especially for the NISAR component of the displacement and water extent products. So there's definitely a lot of reuse and sharing here. Barriers, this really resonates with what Paul just mentioned about getting access, especially to the science team. Many members of the science team are from academic universities that are outside of, say, NASA firewalls, so to speak. So, the current policies in cybersecurity, there are definitely hurdles in getting these systems publicly accessible. one aspect of which is the current policies in authentication and authorization in terms of how do we make the systems more open to access. And this includes both US and foreign national people working with the project. This includes also how present day clearance processes are not necessarily updated to how the complex software that we're developing. The prime example of this is the Jupyter Notebooks that Paul mentioned. With the Jupyter Notebooks, current cybersecurity policies, how do we clear for public release a Jupyter Hub or a Jupyter Notebook-like system where we don't necessarily know a priori the software that will be deposited into this environment for doing algorithm development. So a lot of this goes in line with the whole point about open source science, where if all of the software is open source and open from the get-go, then it would potentially simplify some of the clearance process. But the point here is that a lot of these processes and procedures are not necessarily updated to where we want to be with open source science yet. And actually, quite similarly, as we know, there's a NASA moratorium on new websites. So that is another hurdle in terms of getting more of these tools, such as cloud-hosted Jupyter environments that are publicly accessible to these funded NASA-funded users. Definitely there are hurdles in that. They are not insurmountable, but there are definitely hurdles that could be more streamlined with potentially updated policies and procedures. In terms of opportunities, definitely opening up both the data and platform to the funded users of NISAR is definitely a key point there. I think part of that is actually fostering, as part of the open source science principles here, transparency, reusability, and actually interoperability with other systems, meaning that could the same workflows and algorithms be portable enough to be run by other systems and platforms? I think that will be a good litmus test in terms of how open and transparent and reproducible these systems are. And I think finally, there is this point about an opportunity where right now, the current baseline for the mission is still a systematic processing, at least for the standard products, level 0 to level 2 products, right? As Paul mentioned, the level 3s are limited to the CalDAO sites only. But definitely there has been lots and lots of discussions over the years about, could we do more on demand? Are the next generation of the ESO era missions, are they large enough that could it warrant more on-demand processing as opposed to systematic processing of standard products? These have been ongoing discussions, and I think these are a great discussion, more additional discussions to be had as well. Next slide, please.
2 minutes.
Great. In terms of supporting open science, I think we mentioned a lot of these already in terms of what do we mean by open science. I think it definitely includes what we just mentioned about algorithm development is done open and collaboratively. Data products are open from the start, like what Paul mentioned about no moratorium on the data. Same thing with the algorithms, workflows, and it's reproducible outside. I think the benefits, obviously, is that if this becomes a requirement for a flight project, then therefore it will become in scope, and there will be funding allocated for it to support open science. And I think similarly, if that becomes a requirement, hopefully the cybersecurity policies would be updated to support these as well. In terms of the barriers, I think we just mentioned about the whole, getting it publicly accessible, developing it out in the open, and the policies, that needed policies to allow for that. I think similarly too, just getting all of not just the data system, but the science data system for NISAR is also contributing out to the public open source science. That's like the ICE example that we mentioned. And similarly here in terms of openness, SNWG and Opera is inheriting a lot of these capabilities. I think next slide, last slide here with 1 minute left. So what are the key pain points? I think we mentioned many times along with Paul and Gerald that right now the current policies are providing certain hurdles in opening up the system, especially in the context of open science, getting the on-demand capabilities in these Jupyter Notebook cloud-hosted environments, getting them accessible to more of the science team members. This is definitely a key pain point right now. In terms of efficiency, definitely from a science data systems perspective, it's mainly includes elements of, are we matching up the variability of the science algorithm software that processes data from level 0 to level 2? Are we optimally matching them up with the compute and storage needs so that it's a little bit more cost efficient? Are we exploiting some of the cloud optimized data formats and not just the archival formats that are in current mission baseline requirements, but are we exploiting cloud optimized data formats in the actual production itself? And definitely also there's a potential for additional economies of scale, meaning that if there are multi-mission aspects here of reusability, there could potentially be even more efficiencies gains. An example is, sharing operator workforce, or, can we reduce cloud costs if we were to pull together additional resources across different missions? I think these are definitely additional opportunities here. And I think lastly, this is a key pain point, which is, how do we connect more, bridge the gaps between the algorithm development world and the production world? So there's definitely additional harmonizations that could be possible in terms of bridging the steps of algorithm development to algorithm deployment into the science data system, and then taking the same artifacts and using those for execution in the standard product production. And I think the last point here is that definitely there are constraints in cost and peak throughput that were early drivers in the architecture. One interesting to note is that in the early design phase, many discussions were had about, well, for something this large, we really should be designing in and implementing high availability aspects. But it was actually keenly pointed out, especially by Mayer here, that we need to do what the requirements say, right? The requirements actually do not say that we need high
availability. I have to cut you off so we have time for the questions.
Okay, I'll just end with that. It's a lot of these cost constraints were driving the architecture, and there's definitely opportunities for exploring more on-demand processing. I'll end with that.
Okay, so now it's time for some questions and answers with the Systems Architecture Working Group. Elias?
Sure, good morning. We've got a healthy dose of, can you guys hear me?
Yes, we can hear you.
Okay, excellent. We've definitely got a healthy dose of questions, so I'm going to go ahead and turn it over to Christopher to ask the first one.
Yeah, so when you're talking about cloud environments, particularly the commercial cloud, one of the things that jumps out to me about this particular mission is the data volume. And when you're talking about 100 petabytes of data over 3 years, I was just wondering, are there concerns? And I know this is a pain point for you guys, and you're still sort of, working to tackle this, but are there concerns with long-term cloud storage costs associated with that volume of data?
Gerald, I'm going to throw this back to Kevin. To me, this is on an ESDA side.
Yeah, historically, hold on, I gotta echo real quick. Let me put something down. Historically, and this is going off into the future here, we are, the ESDIS project pays for the long-term archival distribution and management of data from all NASA missions, airborne campaigns, so on and so forth. We've built in the costs related to this, both in terms of the archival as well as the stewardship and egress. So not really.
Okay, thank you.
Next question was from Andrew. Please go ahead. Andrew, if you're on mute, we can't hear you. Andrew McKillis.
Oh, I'm not sure what was the next one. Okay, so this is a question for Daryl. So you mentioned the need to incentivize a culture for OSS and cloud computing. I just wanted to see if you had any additional thoughts on incentives, both from like a traditional academia research, but also industry and general consumer, kind of in the context of data usage and also giving back to the mission in terms of codes and things like that. What additional incentives can you think about be useful?
I think it would actually be good to get a room of academics and others in here to go ahead and say what it would take. I'm kind of trying to speculate, but with any activity where you've got to learn a whole new process, there needs to be motivation. There needs to be something that brings people in with it. To me, the carrots are like roses. Basically, write it into the roses solicitation that thou shall do this, or we're not considering other parts. And that I don't want to be too draconian with regard to it, but we need to come up with a system that does encourage um, coming over and working with it. So to me, early adopter programs are ways. At the end of the day, again, using the old dog, new trick approach, we've got those subset of people, but really reaching out to the up and coming, the new faculty, where basically it's a preferred way of going. We've had discussion with some of the, I'll say, SWAT team, and a lot of the surface water communities actually are already working in the cloud. So I think for those communities, it would be a slam dunk. And so I think each, I'll say, focus area, if you want to go there, or science discipline, is going to have their own ways of being able to incentivize it. And the other part that I brought up is basically the publisher parish. We've got to get around this particular paradigm of basically, if you're getting a promotion, you actually have to have so many publications. In my own personal career experience, a four-page geology publication is going to give you a lot more credit and visibility than a 100-page algorithm type report. And so we've got to basically come up with a way to have a reward system in the publish and perish domain, and also be able to encourage people to say, yeah, it's actually a good thing to share your code. So I don't have any straight up answers. I think really reaching out with the people that would actually benefit from it and seeing what's needed on their part would be the best way of going.
Thank you. Yep.
There was one more question for Paul. I'm not sure who asked it, but I'm going to go ahead and ask it for you. So the community is still convinced that it's cheaper, at least some of the community, that it's cheaper to buy their own systems and download data. Any additional thoughts on why that might be and why they think that from previous run cost studies, from any other information they may have?
Yeah, I think it's mostly related to the fact that they are focused on regional problems where the amount of data that they want is large, but not so large that they can't deal with it. So for example, even I have gone to the ASF archive, and I've selected a region and selected a time interval, which is many years, and downloaded the entire data set. It took like 2 days to do so. This was as a test in my case for a number of reasons. And I know a number of people who are still doing that kind of thing simply because they have the resources and they feel it's just, in the long run, it's a lot cheaper than if they would have to pay for this. And the threat is that they're going to have to pay for the cloud computing sometime when they go to very large scales, and they don't know what that cost structure is going to look like. So there's uncertainty associated with that, whereas they know that computing costs are going to go down over time. If they buy it, every time they buy a machine, it's twice as powerful and the same cost. So that's more of a known quantity for them. So I think our job is to convince them that whatever cost structure NASA comes up with for our computing environment, that it is credibly comparable to what it would cost them to do it themselves. And of course, a lot of academics have infrastructure at the universities that's free to them. So that's another factor.
Yeah, can I just also, this is Hook speaking, I just want to also chime in that from a science data systems perspective as well, a lot of this area was also discussed in the early days, especially with Amazon. One of the key points that was brought up was what they call TCO analysis, total cost of ownership analysis. And part of that was looking at the big picture, cumulative view of what the overall cost of different approaches could be, right? If there are specific users that are preferring to download data out of a NASA archive, right? It may be lower cost to the individual, but maybe overall there are other factors that need to be factored in, such as the egress cost to NASA, or what about the efficiencies of scale that could be lacking because the processing was done elsewhere. As an example, right? There are also other factors like in TCL analysis, who's paying for the actual Ethernet costs, the cooling, the costs, right, of facilities. There are efficiencies gained if there are some, pooling of some of these capabilities. But, a lot of this needs more discussions, but the point is that there is some value in taking a much global view in terms of assessing the true total cost of ownership, say for NASA as a whole, as opposed to a specific project or a specific flight mission.
Gerald has a point, and I'd like to make another point too. So you go ahead, Gerald.
We are at 1:26, and we only have a 5-minute break. So make your point quickly.
Well, I just want to say there are other costs involved. There's the cost of using a system you're not familiar with and not having somebody that you can just call and get things fixed. Also, the fact that they often change configuration and then your software breaks. There's a lot of resistance to that kind of thing. Gerald?
Yeah. A lot of what Paul said, kind of with the uncertainty, I hear that across the board. ASF has been asked to develop a tool to kind of estimate how much would it cost. If you're writing a ROSA solicitation, you got to put in cloud computing. How do you estimate what that is? And then you got spot charges and everything. So it's a lot easier to know, hey, if I buy this computer, this is its cost, and it's only going to cost me power to plug it in. Being able to go ahead and work with that is going to be kind of essential with this to kind of support what Paul described here.
This is Shel Ganneman. I'd like to make one quick comment. I think that all of these cost discussions, I agree with everything that's being said. A lot of scientists, I find, one of the issues is that they're not very familiar with glob storage, and accessing data in this way is a little bit different. It's just not as easy. It's not as clear. We don't understand the structure and how to access it as much. And I would say that some of the open source libraries like have Intake and FSpec have really been making some big advances in this in the last, I would say, 12 to 18 months. And that's an area where I think we need to continue to advance, because we need to make it as easy as possible for people to access the data, because there is this barrier to glob storage that I find a lot of people just try to download it from the cloud just so they avoid that trying to figure out S3 bucket and things.
Yep.
Agreed.
Okay, let's go to the break. Okay, so we're going to get started. Next, we're going to hear from the atmosphere observing system. So we're going to start off with Hal Maring with the programmatic perspective.
Okay, thanks very much. The atmospheric observing system, or what I'm gonna start calling it AOS, is a large and complicated observing system, and so I'm going to spend a fair amount of my talk describing it and then making comments about where I think the complexities and challenges we're going to have in terms of open science are going to crop up. And hopefully the description will also be useful for the committee to get a better understanding and help them in their work. So next slide. Okay, the science goals and objectives. I'm not going to read everything, certainly not by any means, but just the overarching AOS goal is to understand the processing of water and aerosol through the atmosphere and develop the societal applications enabled from this understanding. And you can see that this overarching goal breaks down into more specific goals and then even more specific objectives. And ultimately that leads to a list of geophysical variables we need to get And included in that list of geophysical variables are measurements made, observations made by the program of record. And so what we're proposing for AOS must be augmented by measurements from various sensors that are part of the program of record in order to get us the data set necessary to address these important goals. And so there's the first challenge. Some of these program of record measurements are from satellites from other agencies, and so that there sits a challenge. And secondarily, some of those program of record measurements will be from satellites operated by our international partners, and so that's even a larger challenge. So moving on, next slide, please. I'm not going to spend a lot of time here. This is largely repetitive of what you saw before, but what I wanted to point out here is, okay, so we've got the same overarching goal and we got the same goals that I pointed out in the last slide. But if you look at those columns with A plus CCP, A, CCP, in order to address the larger goal and goals of the AOS, of AOS science, we can't just make measurements of aerosols or just measurements of cloud convection and precipitation, because then we lose the ability to address these processes. And I want to emphasize that AOS is primarily a process study. And so here crops up another challenge. The scale, the geographic and time scale of aerosol measurements and convection measurements and precipitation measurements and cloud measurements are different. And so putting that data together in a way that enables us to address our science goals will be very challenging. It's challenging for experts. It's even more challenging for sort of scientists who are not intimately familiar with this. And if we really want to make this possible for citizen scientists to dip their toe in it, it's going to be even more difficult. Let's move on to the next slide, please. Okay, just to give you a sense for the scope of what we're going after with AOS science, we're going to measure, and the darker orange text refers to things that are primarily aerosol related, although none of these are independent of each other. So aerosol absorption, direct and indirect effects on radiation. This is sort of climate at its most basic level. Low cloud feedbacks on the radiation budget. Aerosol redistribution, movement of aerosols throughout the atmosphere. We'll look at convective storms. We'll try and understand where aerosols came from and how they impact air quality. We'll look at cold cloud and precipitation processes and the high cloud feedback. Now this is the science, the core science of AOS. And again, highly process oriented. Next slide, please. Those measurements that we're going to make for those core science objectives have a great deal of value in terms of applications as well. And I don't mean to diminish applications, because this is really important stuff, but there's also important application to other areas of science, hydrology, for instance. So anyway, I'm not going to read all these, but you get a sense for the breadth of what AOS science and data can be applied to. And because and here comes up another of these challenges I mentioned. NASA scientists and scientists in the university community are used to using DAX and using data in formats that are maybe a little unfamiliar to most folks. A lot of our applications users, they really want their data in a way they can put it into a spreadsheet. And so there's another challenge. Some very complex data in terms of different variables, different time scales, different geographic scales, and being able to give that to folks in a way that they can handle it with relatively simpler computer capabilities. All right, next slide. Okay, here's the sort of overview of the space segment of AOS, and for the NASA only part here, we have two synergistic space segments. The first one is an inclined orbit. It's probably going to be at about 55 degrees inclination. And there are two sort of small-ish or satellites, and they, you can see them, it's AOS 1 and AOS 2, and you can see that they have a radar and a camera, and the other one has a backscatter LiDAR, a microwave radiometer, a polarimeter, and another camera. And I just point out the two cameras because this is another way, in addition to the Doppler radar, which can make direct measurements of the vertical motion in the atmosphere. These cameras will make measurements at different time, of the same place, but at slightly different time because of the difference in the crossover, the movement of those two satellites. And that'll also provide information about process. And in addition to the inclined orbit, we also have a polar orbiting satellite. This is a larger satellite. You can just take a look at the instruments that are on there. Radar, high spectral resolution LiDAR, microwave radiometer, and notably one internationally contributed instrument. This is it's called TICFire, and it makes measurements in the thermal and far IR, which is particularly important for measuring the radiation budget over the polar regions. And so I'm two different orbits, three different satellites, and I think you get a sense for the complexity in the data and how it will be challenging to put that data together. Next slide. Okay. Certainly an eye chart. I don't expect you to measure it. And much of this is repetitive with what I just told you. So in the left column are the satellites and the instruments that go on those for the various satellites I just talked about. There's some more information about the instruments there. What I haven't mentioned is, in addition to the three satellites, there will also be a suborbital, and this will include airborne and ground-based measurements, surface-based measurements. And these are important because there are measurements that must be made that cannot be made from a satellite. And a good example of that are aerosol properties, for aerosol particle properties, for particles located underneath thick clouds. And these are, in fact, the most important aerosols in terms of aerosol cloud interactions. So we need airplanes to be able to go up and make those measurements. So again, it gets even more complicated and more challenging because measurements made from airplanes and measurements made from the surface are very challenging to coordinate or connect to measurements made by satellites. Next slide. Okay, the data system or the data segment will include data processing operations, instrument calibration, software and validation, typical stuff. There will be external elements, DACs, which everyone's familiar with, competed science teams, vicarious calibration, and we depend on the research community to help us do that. The data will come down from the satellites primarily to ground sites, which will ultimately bring the data back to the Goddard Space Flight Center Operations Center. However, there is some data, most likely the microwave radiometer data, that is highly useful for certain applications like numerical weather prediction. And that data needs to get down fast. And so hopefully we're planning on considering TDRS for data with a data latency of less than an hour. Next slide.
This is your 2-minute warning.
Okay, we're very close here. And if all of that wasn't complicated enough, we have potential for, in addition to the contribution of a single instrument by the Canadians, contributions from other international partners. The Canadians also are seriously considering adding another satellite to the polar orbit. You can see that in the Polar 2, and that's got 2 instruments on it. These are limb sounders that look at aerosols and moisture in the upper troposphere, lower stratosphere. In addition to that, there's potentially a JAXA satellite, which will go in the inclined orbit and will have a wide swath Doppler radar. This would be a huge advantage for us and essentially gets us a GPM follow-on for very little cost. In addition to that, the French want to add 2 microwave radiometers, and if they do that, we'll take the NASA microwave radiometer off and put on one French microwave radiometer on the JAXA satellite and one on the AOS satellite in the upper right there on the inclined orbit. And the purpose of those 2 satellites is just like those cameras, to look at the same scene with a time difference. And this will get us some additional information because this will be a shorter time distance and get us a chance to look at processes that operate on a shorter time scale. Okay, my last slide. There were a whole bunch of questions. I hope I've addressed a number of them, but there were 3 more that I thought I should address directly. How does open science fit into your program? I think it's really obvious. With the complexity and the magnitude of the data that we'll collect, we're going to absolutely need national and international science community to wrestle with these problems, and making the data available to them in a easily accessible way is critical. What investments are you making toward open science, and what are expected outcomes? We're not making any investments yet. We're still in pre-phase A, but this workshop, I think, should be seen as an introduction, at least as far as AOS is concerned. And I encourage the SAWG to stay connected, even in small scale meetings with us and informal interactions. Those interactions can be very helpful in terms of getting this AOS data set made available. And then lastly, what barriers across NASA that inhibit participation to open science? I've already mentioned that the suborbital measurements and the combination with the satellite measurements will be very challenging. And measurements made by our international contributed sensors in terms of getting them to be open science the way we'd like them to be may also be challenging. So that's it. I'm pretty close, I think.
Yeah, thanks, Hal. Scott,
Sure.
you're next. Ready when you are, Scott.
Yeah, I just had to unmute. All right, so go ahead and move to the next slide. I just wanted to go to the next slide and advance it. There we go. So I just wanted to bring this slide up again, just to reiterate what Hal said about the complexity of this mission. We're looking at 10 different instruments just from the US or the NASA contribution plus the TIC-Fire instrument. And we're considering additional contributions from international partners. It's a lot of instruments. It's going to lead to a lot of products. And that certainly adds to the complexity of what we're trying to do in terms of the science and the algorithms that have to be produced and the range of products that will be produced. We're considering not only products from the individual instruments, but how different instruments can be combined synergistically to get the best possible information on those geophysical variables that Hal had mentioned. So go to the next slide. I tried to just schematically show the flow of the products here, starting at level 1 from the different instruments, and I'm only showing for the instrument types. We have these 4 instruments in both the polar and the inclined orbit, although with somewhat different capabilities. And then we have the cameras and the spectrometers that I haven't shown here. But it just gives you a sense of how we may have multiple level 1 products, typically a relatively small number. But this will flow down to a set of single instrument products. In some cases, data will be combined from different sensors to produce a set of synergistic products at level 2. And then all of these will flow down to level 3 gridded products, typically probably gridded on a monthly timescale or something to that effect. The level 1 and in some cases the level 2 data will also be pulled into atmospheric data assimilation systems along with the program of record to lead to assimilated products that are basically a combination of the observations and the models that provide comprehensive information and fairly complete information. Now, we are just in pre-phase A. The science team has identified many of the single instrument products that they're interested in and is currently working on identifying some of the synergistic products. It's going to be a lot of products, and it'll be difficult to get all those done by launch. So one of the things that we're going to focus on is identifying those products that are needed at launch that likely will have high heritage in terms of algorithms versus things that need a lot more theoretical development and algorithm development that might be viewed more as enabled or experimental products and might end up being put together after launch when we have a funded science team. Next slide. So here is just a listing of some of the products from the different instruments and the different inclinations, as well as the data rates and total volumes of data. For what we've identified so far, which is primarily the single instrument products, and all these numbers here are very preliminary, we're at about 5 petabytes per year of volume. But again, we haven't fully scoped out the synergistic products, and that will add to this volume. We are hoping that as we identify synergistic products that we pretty much feel certain will be done by launch, that they may make some of the single instrument products redundant, and maybe we can reduce some of those products. But this at least gives you a feel for the overall data volume. Next. In terms of applications needs and latency, so during the ACCP study from 2018 until the beginning of this year, we had science and applications teams that worked to define the requirements for the missions, and the applications team worked, really reached out to the community to find out what the needs were and they identified several different science focus areas, including weather forecasting, disaster modeling, excuse me, and monitoring, and health and air quality. And they looked at the latencies needed to do these different applications. And now with all the different instruments that we have, we certainly can't do all of these at sort of the 1 hour latency rate. It would just be too expensive. So we had to prioritize. And it was recognized that from the passive microwave radiometers are already used in level 3 products that have high visibility, are used for a wide range of applications. And so it's really essential to get those down in near real time. A number of other products from the radar, polarimeter, and LiDAR are of high value, but probably not needed with as much urgency. And so the goal is to have those products out to users in sort of the 3 to 6 hour time frame. And then the spectrometers and probably the cameras, we expect, they're high data rate instruments, don't necessarily have immediate, they have applications, but maybe not as urgent as for the other instruments. And so they may be more on that 6 hour or more time scale. Next. So I wanted to address some of the questions that were in the template that we were given here. What we envision at this point is that the ROSES funded science teams probably won't be in place until around launch. And so that means that much of the product or algorithm development will be done by the mission funded teams. And that's fairly limited resources. So again, we'll have to define a set of standard at launch products that typically will have high heritage. Also prioritize some of the international partner products. And we may have to leave some exciting combinations of data sets but ones that are lower heritage to be more experimental or enabled products that would get done once we have a fully funded ROSES science team. And that data would then be also available to the wider community for product development or algorithm development. In getting ready for launch, we think it'll be really important to have an analytic collaborative environment or basically an early adopter program where we engage the modeling, scientific, and applications communities, give them simulated data sets so they can prepare to use data at launch once those data sets are validated. And we expect to have the data sets available to users fairly quickly after launch. I mean, obviously there's a period of initial instrument checkout. There'll be certain calibration activities that need to get done. But as soon as possible, we expect to release a set of beta products that will have a minimum level of scrutiny to make sure that everything looks good, that there aren't any obvious artifacts, but will come with warnings to users that these haven't really been fully validated at that point. And then as we collect data during that first year, we can do some partial validation by comparing to either other satellite data sets or suborbital data sets to at least show that the retrievals are more or less behaving or have the skill that was expected. You need a certain amount of data to do that. So probably it's within the first year, and we would eventually promote products to provisional status. And then they'll get promoted to validated after they're fully validated and quality checked. That more than likely will require more than a year of data, particularly for our instruments that provide data just at nadir as opposed to a swath. That means more limited opportunities to match up that data with ground or suborbital assets. And so those products will gradually be promoted to validated in sort of that 1 year to by the end of phase E timeframe. Next slide. Just touching upon applications again and how we might grow those applications. As I mentioned before, we've already been pretty engaged with the applications community because a lot of the measurements that are being done by AOS have heritage with CloudSat and Calypso, TRIM and GPM and other missions. There are user communities that are already in place there. So we've been reaching out to them even during the earlier study to assess what some of their needs are, what the latency requirements are, what sort of product formats that they might need and things of that nature. Based on that input, our applications team has already put together a draft community assessment report, which is currently under review. And then looking forward, we're just going to continue to reach out to these communities to to understand what sort of tools they're going to need and how we can interact with them in terms of getting them ready for products, how we might tailor some of these products to their needs. For example, a lot of our applications users use the gridded products that may be on a monthly timescale. In some cases, like for precipitation, they're on even a half-hourly timescale. But we want to make sure that we're providing tools for analysis, providing formats that are appropriate, and so on. And this is where an early adopter program is really critical. Next slide. In terms of Cal-Val activities, so each of the DOs is expected to have a suborbital component. And we have been looking at that and really trying to scope out the full range of approaches for suborbital science. And as part of that suborbital science, which focuses on what the science we might not be able to do from space, we're also looking at how we fold in Cal-Val activities with that. We envision several different pathways to doing the suborbital science. One is through global or regional scale networks. This may be data sets such as the radar network over the US or MPLNet, AeroNet, and things like that are distributed globally that are longer term so that we can do comparisons in different regions. There may be super sites that we can use. A couple of examples are the ARM super site, and at Wallops Flight Facility, we have a precipitation and cloud super site that we've been using for trim and GPM. And so that, again, this allows for more focused science in a small region, but where you have a much denser set of observations and maybe a more complementary set of observations. And then there'll be targeted airborne campaigns and such, where we are trying to get more information to improve the algorithms and validate the assumptions in the algorithms, as well as validate the products themselves. And an important part of this is making sure that we have adequate airborne or ground-based instruments that serve as satellite simulators, and then in connecting that to the algorithm, making sure that we have numerical simulators so that models can be used to create simulated data sets. Next slide. There were a couple questions here I tried to address in terms of how we'll support open science and documentation and things of that nature. You can see the question in yellow there. Part of this, for those of us who have been involved in past missions, I think this requires a bit of a paradigm shift in moving to open science, particularly when it comes to some of the algorithm development. We've often have funded and produced the algorithms in-house, sort of within NASA, maybe with a limited set of universities, and then eventually with the Roses funded science team to go more broadly than that, and to be able to readily incorporate input from general users may require a shift in how we actually implement these into a data system. But again, having an early adopter program is useful. We'll make sure we have ATBDs out for all products and try to provide a range of ways of sharing information, whether it's through documentation, forums, website, and so on. In terms of a common framework that can help amplify the project science objectives, I think open science is a good way to do this. What we found in trim and GPM was that the mission is focused on a smaller set of products, and the user community often comes up with new ideas for products that may be combining different data sets within a given mission or combining one mission's data set with others. This may be creation of databases that might be synergistic in that they're taking elements of different missions and combining them, or they may be focused on different phenomena, such as precipitation features, looking at tropical cyclones and things of that sort. And I think having an open environment is a great way to do that, and a great way to share data across the different missions. Next. And then in terms of whether there are any constraints or barriers and such that we'd want to make you aware of. I mean, as we've had discussions about open science, one of the top questions that has always come up is how do we deal with proprietary or competition sensitive code? I know some of our instrument teams, who have to compete for missions now and in the future are often concerned that by sharing their code, it's giving away their trade secrets, and that may be problematic for them in terms of making it easier for outside communities to replicate what they're able to do, and put them at a disadvantage.
Wrap up.
Yeah, there's a couple more questions here. So does open science mean unsolicited or outside mission participation in at-launch algorithms, or is that something that really is more toward the post-launch era? Not quite sure how we would pull in outside of mission information where people don't have a requirement to deliver code at, on time and in budget. So that might provide some constraints. Supporting open science could put a burden on the missions for user support, people who aren't familiar with the code and always have questions about the code, and who's going to respond to all those questions and help them along. And one other topic that came up after I had submitted these slides, one of our team members was asking about science participation in this study. It seems like it's very heavily on the data system teams and such. And if this study is driven primarily by the data system teams, independent of instrument modeling and analysis communities, the concern was that we could end up with tools that do not necessarily meet the community needs. And so at what point do you try to get input from those communities? So I'll stop there.
Okay, thanks. So Robert Wolf, you're next. Robert, are you here?
Okay, now we're unmuted. So I'm Robert Wolf, and I'm going to talk about the science data segment portion of the AOS for this AOS mission. And my co-authors are Kurt Tilmas and Dave Myers. So this is the overall system architecture that we're using. And if you think about all those things that are inside of the box, this is what we're doing in our science data segment. We're receiving the data, we're developing, we're supporting algorithm development and validation. We're doing the data processing. We're storing the outputs and providing access to data. And we're also doing quality assessment and generating reports and statistics for what we've done. The main thing that seems to be changing in the new discussion of open science is, how do we interface with these this analytic collaborative environment? So the current system is somewhat closed. You could argue actually it's fairly open already, but in the sense that we don't really have a good mechanism for bringing in users' input into the system, and we don't also have a good way of allowing users to use some of the same tools we use in production and QA and validation that our science team members have access to. We also have up in the upper left corner or right corner is the external partners. We have a couple, at least the Canadians and perhaps other external partners who will be possibly doing some of the processing. We would give them, I think there's a mistake on this slide, it should be level 0 data goes out and we would receive their level 1 and level 2 data products. And how do we incorporate those partners into this open science environment? And I think this goes to some of the questions we had yesterday for Kevin Murphy when we were talking about, these partners, what types of things can we do with the partners to make sure that they're able to produce their software and processing in the open as well as we can with our science data segments for our users. Guess that's pretty much all on this slide. The next slide shows more of a breakdown in terms of internal data system. So basically, you have data coming in and data going out, and then within the science data segments, you have processing capability, an object store, a software repository, and production databases. And all of those feed the production system, which is an orchestration or a scheduler that basically runs all of the algorithms in sequence. When when the data arrives, it kicks off the level 1 algorithms and then produces level 2 and level 3 products and so on. And a lot of those are driven by production rules. And we've kind of shown in the center there that there are several instances of this. So there could be one for forward processing, another one for test, another one for reprocessing. And one of the things I think we're talking about in this open science environment is allowing users or our users to spin up something like a production system and actually run their algorithms within it. And Hook actually showed this probably in a little bit better way, but we're thinking about something very similar for the AOS mission and showing being able to actually duplicate this environment and then run their own software and produce similar products. So the thing that I think may have changed yesterday based on some of the discussions is how closely coupled our internal object store is to the DAC object store, which I think is probably somewhere in the analytic collaborative environment. How do we couple that with the tools and so on necessary for the users to use that? So we can go on to the next slide. So in terms of our implementation plan, there will be early development of simulated data and processing in this collaborative environment. The algorithm software will be decomposed into usable parts. We have libraries, executables, etc. Sometimes we'll be sharing those parts, like a library across multiple platforms. Some parts may come from legacy systems or heritage systems, and each algorithm will have to be analyzed and decomposed and essentially written in software. The software development within the software repository, and there will be an automated continuous integration, delivery, and deployment process within that, something like GitHub with the various capabilities there. And then production will be based on the algorithm software that's fully integrated into a runtime environment with container images that can run across multiple platforms. So the idea is that central engine there can run these containers, use production rules and so on to produce the products. Similar to what we do right now for Modus and Veers and OMI, OMS, GPM, etc. The legacy missions that we've identified, Scott showed a chart of all the number of algorithms and so on. There's a lot of legacy missions that we can leverage in terms of the algorithms and the algorithms for the products, particularly level 1 and level 2 instrument only products, Modus, OMI, GPM, CRIS, etc. So we've got a lot of legacy missions and possibly can leverage a lot of legacy software and even legacy data processing approaches for AOS. Next slide. So this is a schedule. It's a very preliminary schedule, and we've got some more details that we could give you. But really, we're actually in the pre-phase A time period right now. But once we get into and we're looking at the preliminary architecture and concept of operations, our preliminary requirements are how we're going to be doing verification and validation. And then once we get into the phase A, we'll be doing our preliminary verification validation plan and the configuration management plan and so on. And that's where we'll start seeing some more definition of the algorithms and understanding better what the requirements are for the actual processing system. And then for KDP in phase B, we'll be doing defining the at-launch processes and products and drafting the early ATPDs, preliminary design review. And at this point, we'll probably start seeing some code start trickling across the divide between the into the science data segment. And then we have a critical design review in phase C, the phase C, and then we get to launch back in 2028 for the inclined mission and the polar mission in 2030. I think one of the things I didn't show on this is that the various builds of the system, I think we'll have something similar to what Hook showed in terms of multiple builds of the science data segment with various levels of algorithm maturity and simulated data and so on, and the various phases of that. Next slide. So in terms of supporting open science, well, first of all, I'm going to say something fairly controversial. I think we've been doing open science for many years. I think you could argue that even the EOS missions starting 20 years ago have been doing a great job of making sure that the algorithms are available, they're peer reviewed, that and even the code is available for a number of the instruments, as well as the products are available as soon as they're produced and as soon as they're of sufficient quality for use. I think what we're talking about in terms of what's new is things like doing this in a cloud environment, using modern tools like the Git capabilities in terms of being able to very easily incorporate contributions from the community, and then also making the tools more generally available that currently are mostly only available to the science team to actually work with the data and manipulate it and actually do new things with the data. But anyway, so in terms of supporting better open science, or I think we will be supporting open science. It's a collaborative environment that's enabled by technology and the better sharing of data, information, and knowledge about what's going on within the system, and hopefully accelerate the scientific research and understanding. And I think one of the things that with the number of synergistic products that are going to be produced for AOS, I think open science is a real key to doing that. I think
2 minutes.
I'm sorry?
2 minutes.
Oh, sorry. Okay. So in terms of the other questions, given legal rights and so on, I think we're going to be, our data will be in an open object store, and we'll have to figure out how that's going to work with the DAX and CMR and so on. There's quite a bit of details there we need to work. Open source code, we're going to make that all available in a repository in this analytical framework. And we'll be using container images to do our data processing, and allows us to be reproducible on multiple platforms. And we're going to do as much as we can to develop the software in an open manner with full transparency. Next slide. So, in addition, we hope to provide. Well, this is one thing we'd like the committee to consider, is that any new processing software framework or architecture should be developed in a way that it's not just one standard solution that fits everyone, but it's an extensible solution that can be adapted and adopted by the different data producers. And we do want to make sure that there's a standardized interface from the algorithm to the processing framework that encapsulates the runtime environment, so you can plug in any environment and has really flexible production rules. So I think that's all I have. Thank you.
Thank you. So now we have time for questions and answers with the Systems Architecture Working Group. Elias?
Sure, let's go ahead and go to our first question, and I'll ask this one. Since AOS is going to be sharing lots of data with other sensors, are you planning to also share the algorithms as well across these and do some maybe processing of some data that you're going to bring in to your system from other sensors?
Well, yeah,
someone's trying to.
Yeah, some of the data sets we're going to be using, NASA, like for example, the geostationary data, we may be developing our own algorithms for cloud and aerosol retrievals. And I think we'll try to be consistent with the policy of open science to share those algorithms with users. Other agencies' algorithms we can't necessarily share unless they provide approval. And so we may be adapting our own algorithms as needed. But that's still to be determined yet exactly which products we'll focus on and what we'll do. With microwave observations, like with GPM, we've applied our own algorithms to level 1 radiance data, and we may do something similar to that. So you don't necessarily need their retrieval algorithms. You may just need their level 1 products and then apply it to our own algorithms. I don't know if that gets to your question though.
Yeah, yes, it does. So you're going to make your algorithm shareable as best you can, and hope that if you need to get other algorithms that they are available. If they're not, you'll have to re-implement them. In that same vein, what about the data? So you're bringing in data from international partners and so forth. What's your plan? Is the plan that all this data will come in and you'll bring it into your cloud system and do your processing? Are you somehow working to share that data across, and keep it wherever they're going to store it? What's that plan for AOS?
So in terms of the international partners in the mission, I think we need to reach agreements with them, working through headquarters. I know the way it's worked, say with TRIM and GPM with JAXA, was that they did not provide their level 1 source code. They would produce the level 1 products, and then we would have level 2 code that we could share, but we could distribute level 1 and higher products. So it all depends on what those partners are comfortable with in terms of sharing, and Hal mentioned how that complicates the idea of open sharing, that here in the US we might be fully for it, but other international partners may have concerns about fully sharing, and we'll just have to reach an agreement with them about what can and can't be shared.
Yeah, I think in terms of reproducibility of the algorithms and the products, that we have to be able to allow as much access to those data as possible. So I think if you have one ancillary data that users can't get, and so they're not going to be able to produce our products, and so I think that's something for headquarters. Hopefully, we can get some help us with getting those types of agreements and so on in place with our partners.
Yeah. It sounds like your current plan is really to copy as much of that data, bringing it into your system so your users can use it. If there's an opportunity for sharing, obviously that'll make it simpler, but your current plan is to just copy and bring that in. The next question was from Wen Ying. Go ahead, please.
Thank you. I think you already touched on some of the fronts of this question we're going to cover. So I think in the presentation, it was highlighted that AOS is, one of the main objectives is to do the process studies. And as we all know that to accomplish that, the spatial and temporal correlations of data from different instruments are crucial. I guess my question is how this is going to be addressed by the AOS. I think the multi-instrument products probably is the answer for the process studies. And my question is, will this multi-instrument product including the data from our international partners and how the data is going to be, bring in? Is there any, international data sharing agreement in place for this?
Yeah, I mean, certainly with the synergistic products, we will be, I mean, we're in the process right now of defining what those products would be, primarily focusing on the AOS, the domestic instruments at this point. But we do envision that as, with time that we will, scope out those other synergistic products. The one area that we are working on at the moment is with the CSA and their tickfire instrument that will be used in combination with a shortwave spectrometer and other instruments to generate radiation-related products. The main idea is to be able to get these measurements as coincident in both time and space as possible. Obviously, if they're on one spacecraft, that works better than others. The other way of getting at processes, as Hal mentioned, was these time difference approaches with the cameras and the radiometers, where the time difference is on the order of, say, 45 seconds to maybe a bit over a minute. So you're looking at these very short-term changes that reflect the processes, and then coupling that with the other instruments that are just measuring at a single time. But again, the synergistic products are being defined now, and I think as we get into phase A, we'll have a better answer for questions like yours in terms of the details.
Next question was from Hook. Go ahead, please.
Yeah, actually, this question is kind of actually related to a topic that was brought up yesterday. I think it was Luke that mentioned about, there could be some graying areas here between the roles of a flight project science data system with the roles of Estes DAX. I think this is a question with respect to the pre-launch analytic collaborative environment where it's recognized that on the front end, at least, there's definitely some overlaps between what's being described here versus what, say, some of the DACs traditionally provide as services, analysis services to the end user community. I was just curious, like from an AOS perspective, are there any considerations for potential like open sharing or collaborative roles with DACs and even with other missions? Since I think a lot of missions are beginning to talk about, really similar analytic collaborative environment concepts.
Yes, I think with the DACs in particular, I think we're going to have a much more streamlined process if we're sharing as much data as was talked about yesterday, including the simulated data and various, intermediate products and things like that. I think we need to be thinking about, how can we streamline the process of getting the data into not only the DACs but CMR, but also really labeling the data appropriately to say that this is test data, this is not the standard products, this is not meant for science use. It's really just as a kind of a way of opening or giving more transparency to our process. I think the downside of some of this may be, data may be used inappropriately. People may pick up a test data set and write a paper on it, and I think we should try to make sure that we provide all of the flags and things like that to make sure that the users don't publish something by mistake or use something in an application where it's really not appropriate to do. So the labeling and of the data is going to be really important. I also think from a design perspective, how do you estimate some of these? I think for test data, we can probably come up with some idea of that, but how do you make sure there's enough resources to store all of this data, especially if you're asking for these intermediate data sets that aren't typically stored. So I think there's some cost implications, there's some usability implications and so on. We just need to be thinking about all of those as we try and make our data sets and algorithms and so on as transparent as possible.
Okay, are we ready to get started again? So our next topic is the mass change mission, and we're going to start with Lucia.
Yes. Can you hear me?
Yeah, I can hear you.
All right, great. This is muting and unmuting instructions are a little strange.
Yeah, we can hear you. So whenever you're ready.
Okay, so I'm the program scientist for mass change, also the program scientist for the Grace Ballon mission that's operating now, and for that I manage the science team for that mission. So just wanted to provide a few programmatic science perspectives, and then give David as much time as possible to get to more detail on the processing of this measurement. First, I would like to briefly remind everyone, please go to the next slide, what is mass change, why we care, and how we measure it. Mass change is the mass redistribution in your system at different scales. Global mass transport measurements are critical to understanding climate processes, and when we use it together with other data, this data allows us to relate components of the Earth system to each other. The mass change is essentially a measurement of the Earth's gravity field, and it needs to be accurate enough so you can actually measure changes in the gravity field at different temporal and spatial scales. And it was first demonstrated by the GRACE mission, which launched in 2002, was the first ESSP NASA mission. And it was a mission of two twin satellites tracking each other. Now we're 2 decades after that. We've had the GRACE follow-on mission continuing that record, and the next ESO mass change mission would also continue the satellite-to-satellite tracking record. That essentially will be the same type of architecture, but hopefully and possibly we can improve that record by adding a second pair of satellites. Those will be again a twin pair in an inclined orbit, as opposed to the polar orbit that the first satellite would be. Next slide, please. So the vision for open science and the definition that I see here is obviously in perfect agreement with the science management perspective, specifically and most importantly in the purpose of it. The purpose is aiming to advance research and science understanding is the core of the science at NASA. And I would also like to add here, I made that comment to Nancy, I think she said that yesterday, adding in that definition, extend the user base and applications. So how do we actually materialize this? For science management, the key objective is to optimize the effectiveness of the funding and the resources we have. So basically, we select research through competitions primarily. That is mostly our vision and implementation process, so that we can get science done that has the most impact. And we can fund the best and more return for our money and the taxpayers' funding with actually in the near term and also the long term. We can understand and appreciate the impact of the funding that we use. And I would say at large, our community is a collaborative community. It generally has an open culture. We have funded, broadly solicited 5 different science teams for mass change for this mission data. And these were done through open competitions. We participate in community forums like HEU. One thing I wanted to point out here, there's a newsletter from the project that goes to a large community And this is basically users that they see that show an interest in the data and download data or inquire about data. They add them to the distribution list. So they get to find out what is new with the data sets, what are new publications. They advertise the science team meetings and so on. So I just, I'm hearing perhaps sometimes in these discussions about opening the science teams meetings, and one who doesn't know would think you need a secret code to get through the basement door to get in and everybody's out, and it's really not exactly like that. Our science teams are quite broadly advertised. People do have to register, but other than that, it is an open culture. In terms of barriers, I don't like the term barrier in the sense that it implies some sort of an intentional impediment set up there to inhibit open science, as it says here. I think what I would like to offer here, and what I do have in the slide, are some unique points about this data set that it should be considered when one is looking to implement improvements. So first, it is the gravity measurement and the core processing. Because of that, it is done by a highly skilled, very small community of experts globally. But once you get through the core processing and you go to higher level products, then mass change becomes a very much so multidisciplinary measurement. So more and more disciplines and communities and users come in, the higher your data level goes. So that is really one very key thing to consider, and I'll get back to that. One point that I would make here, and something I do not agree with, was the NASA policy to not release mission data until several months after the IOC has ended. So it took several months for the community to get data sets. I think the benefits from doing that early, even though the data still has some issues that haven't been cleaned up by the project, the benefits, I think, outweigh the problems, in my opinion. So that is one thing I would recommend here. And next slide, please. So in the vision for data processing fundamentally goes back to this principle. Given the resources that we have and the funding we have, how do we maximize the science impact, both in developing new understanding and also extending the data to new applications. And that draws back to the idea of having unrestricted access to data and tools, but also avoiding duplication of efforts. I would not want every grantee in the science team to basically reinvent the level 1 and level 2 data. I want as much of that fully validated standard data set distributed to as broad a community as possible, so we could get to advance the science, to advance the applications. One thing I would envision for the mission data processing in general is to have some flexibility to allow for evolution in the observations and the observing system. And for example, in this case, one thing we know now, that we could potentially, as I mentioned, go to a double satellite pair constellation. It would be great to have a system that could, is flexible enough to adapt to that quickly. And I would also add, I don't know if it is clear from the bullet that I have on this slide, it is the fourth bullet, this flexibility to allow maybe studies of future architectures to be easily done through this processing system. There's so much skill and knowledge embedded in these processing systems, it would be good if there are actually a resource for people to do architecture studies and also open it to a broader community as opposed to only, NASA Center team. It would have been nice to have, a broader community engaged in that architecture. So my last point here, and of course that's also from my experience with this, our missions for mass change and also the future missions where we have discussions with international partners. It is here in red. I like to emphasize this, that they need to be interfaces with other agencies, other partners. So, if there is a mission partner, obviously it involves a low level data processing, and also on the higher level and international services. There are services in Europe that are looking to implement operational products from mass change, like quick drought forecasting type of product. It would be nice for users of NASA data, not just the PODAC or the NASA system, to actually have interfaces that can look at these data sets and somehow get connected without having to search on their own, but just find them when they're looking at the NASA data. Next slide, please. So with this, the next two slides, I'm not going to explain in detail. I just want to make, to demonstrate a couple of the points that I made before. You look at the row mapping of the gravity field on the left map on this chart. This is basically errors because of the observing geometry. This is not the monthly gravity field, so we do need to process it. And that is the middle map where you basically do what we call destriping, the aliasing of these artifacts in the data set. So the point here, we don't want every user, do we want to take steps to distribute that software and have resources spent on that when we really don't need necessarily every user to engage in this particular effort. And that is strictly the point we want to make. The next slide, it's here to demonstrate the complexity of going from the level 2, which is the monthly gravity fields, to level 3 and level 4, like gridded data sets. For example, for underground water, one of the most popular data sets that's being downloaded. So there is a lot of processing that happens here, and there's a lot of skill. How open do we need that software and distributable? Perhaps strategically, we want to think about what software we distribute. And I want to point out here the box to the right, 7% of the GRACE follow data users, they're basically downloading level 3 and 4. This was just reported in our science team meeting from the project. So
2 minutes.
Oh, sorry. Okay, next slide is my last slide. I'm not going to repeat the same recommendations. What I want to suggest here is my last bullet for this working group to implement the equivalent of a market research approach to basically develop pilot projects to demonstrate that indeed we take some of the steps that you're going to develop and we reach our goal, which is to accelerate science research and understanding and applications. We know how to measure those. We track research publications, so do the NASA funded scientists increase their output, or do we get a whole new of publications that use the NASA data that come from non-NASA funded investigators? And I would add that we already track some of these metrics. This should be a thing to demonstrate. It will help the team and the agency correct perhaps the steps that you're developing to implement for this initiative. And that's all I have. Thank you very much. Next up to David.
Thanks, Lucia.
Okay, thanks, Lucia. So I'm going to follow on now. Actually, I'm going to be doing the next two talks. Our team was stretched a little bit thin. We had the GRACE follow-on science team meeting last week, and then this week, both yesterday and today, so we have a bit of an overlap. So I'll talk first about the science perspective and then the data processing. And we followed fairly closely the template because we thought these are really the questions that are being sought after to help make decisions. So next slide, please. So in terms of requirements, I think that first bullet point, our requirements are probably less than a lot of what I've heard. Our data rates and data volume are fairly low. On GRACE follow-on, it's about 380 megabytes per day. We do have some needs in terms of processing. So we do rely on supercomputing resources to process gravity fields and mass change fields. And there's also large amounts of kind of intermediate data storage required. So we have a local compute cluster that's currently used. It's 500 terabytes and mostly full. Again, that doesn't rival the 100 petabytes that we heard earlier from some of the talks. So this might be considered small. In terms of latency, I think that's still TBD on the final architecture. As Lucia said, whether we have one pair of satellites or two pairs of satellites, I don't think we consider that to be a driving requirement. We currently have capability to produce quick look fields. We call them quick look with a 1 day latency and processing time. And really what drives that is actually processing of the entire GNSS constellation, both the orbits and the clocks. And they have kind of a rapid product that is fed into our data processing that we pull. Okay, in terms of expected data products, we have level 1, level 2, and level 3 data products. That would be the responsibility of the project. To give you an idea, the level 1, are more raw. Not many users interface with level 1. The level 2 data products are still a bit esoteric. They're in units of spherical harmonic coefficients, normalized geopotential. So that there's, again, at that entry point, there are still a fairly small set of users that interface with the level 2 data products, but those expert users are able to make their own level 3 data products and perform scientific analysis on those level 2 fields. And we see a lot of that in the science team and among the community. But the level 3 fields, those are gridded mass change fields, surface mass change fields. And like Lucia mentioned, that is where most of the action happens, where people are really interfacing with the data and producing synergistic Earth system science. Level 4 data products are not a requirement on the project, but we do note they carry a high value. We currently do, the GRACE follow-on project does produce a handful of level 4 data products we call climate indicators, and those get a lot of downloads. The next bullet, what's the plan for algorithm development, analysis, and CalVal? So for algorithm development analysis, we have a very mature science data processing system that has been really fine-tuned over the last 20 years. Some complementary algorithm development and evolution is required to combine, 2 pairs of satellites or even 3 pairs of satellites, depending on the final architecture. But those algorithms exist, already. They just need to be kind of integrated into the larger science data processing system. So there is a little bit of work left to be done there. CalVal is a topic in and of itself, and I'm going to punt that to the next slide. And I'll talk to the last 2 bullets first. Actually, we can just, let's just talk CalVal right now. Thank you. And then we can go back. So calibration and validation is a challenge for mass change. Mass change is uniquely sensed in the Earth system. There's no other way to sense it except by measuring the gravity field of the Earth. And so that really limits the validation strategy to similar space observations. So the best form of CalVal is to have overlap with GRACE follow-on. And then we can compare GRACE follow-on mass change fields with mass change fields from mass change. There are external validation options that have been used. They are used. They were used in GRACE follow-on post-launch to make sure that we had confidence in our fields. And those, there's a long list of those where we use other geodetic observations, satellite laser ranging, GNSS observations. We use some in situ observations, ocean bottom pressure recorders, or GNSS data on the surface of the Earth. Other synergistic, observations include satellite altimetry. That's very synergistic with mass change, looking at altimetry, height change over the oceans and the ice sheets. And then there's also models. There's kind of terrestrial water storage reconstruction products and mass models of mass variations on the Earth. And so we can use really all of these tools to help calibrate and validate the gravity fields. And it's really worth pointing out that that list right there also captures areas of synergy that are very ripe for addressing Earth system science questions when we view all of the data together in a common ecosystem, kind of at the level 3 data product level. So if you can go back one slide, I'll talk to the last two bullets. Yeah, so who needs access and when? Okay, the project needs immediate access to the level 0 data, the instrument team, the flight ops teams. And then we kind of talked about latency already. Quick look fields are really a 1-day latency, but typically the level 1 data products have a 14-day latency. That's driven again by the GPS, the GNSS constellation, kind of final orbits and clocks. There's a processing delay there. And then that flows down into level 2 gravity fields, which are typically at a 40-day latency. So what is the plan for the groups to collaborate and share information and code? So as Lucia mentioned, I think our what's the right word? So our SDS processing centers have a very rich history of tight collaboration on intellectual topics. We have historically not shared code because each SDS center has their own unique software packages. And what we have found is actually that is an asset, a very valuable asset that contributes greatly to V&V. And so we have leveraged that diversity in software to improve data products in the past. Okay, next slide. And one more. Okay, so how will our data products be generated? Really based on past mission experiences and successes. I'll punt that to the next talk on the science data systems, where we go into a little more detail on that. And then who is expected to generate those products? For level 1 at JPL, we generate those products. For level 2, we have multiple processing centers. So both at JPL, the Center for Space Research at the University of Texas at Austin, and then Goddard Space Flight Center, and then our partner currently on GRACE follow-on. It's been GFZ in Germany. That was the same for GRACE. But if we partner with ESA, then of course there would be other SDS centers that would join that group. The level 3 fields would be produced at JPL, but this is also where the user community comes in and contributes. They can make their own level 3 data products, and then level 4 plus. Again, is where the user community contributes greatly, but the project can contribute to that in a meaningful way. So what resources would product generators need? Really, for level 1 through 4, it's appropriate data and software. And just note on level 2, again, supercomputing resources are needed and large amounts of intermediate data storage. In terms of portability and license issues, the existing workflows they have limited portability and openness right now. The portability is actually fairly straightforward to address with software engineering practices. We're currently actually doing that for GRACE follow-on. so we can port our code easily to different supercomputing systems to make gravity fields. In terms of licensing issues, for Grace follow-on, Caltech considered the code developed at JPL to be proprietary. So source code was not released, but in lieu of that, an algorithm theoretical basis document, or an ATBD, was released. So it's worth noting that the software suites at JPL and Goddard and Texas at CSR really have been developed over the last 50 years. They go back to some of the first missions on the moon in terms of just orbital mechanics and how we land a satellite on the moon. Those are the same principles that are used to make a gravity field. They consist of hundreds of thousands of lines of code. And at least in the Grace and Grace follow-on experience, there has not been a clear need identified to make that code open to everybody. It would actually create quite a burden on the project to provide software support and documentation. So how does the level 3, moving to the next bullet, product support Earth system science? This is really where we see great support of Earth system science. So the level 3 products are where we have the synergies with other observables. Data assimilation is very important. Mass change data gets assimilated into ocean circulation models, also land surface models. But that's not the only way. So, creation of this mass change climate data record really at the level 3 level of data product is critical for Earth system science. In terms of pain points, Lucia mentioned this already, but the complexity of the data processing at level 1 and level 2 really requires users with significant expertise. And that expertise, it's not software engineering, although that helps, and it's not a data science problem. It requires someone with knowledge, in-depth knowledge of orbital dynamics, estimation theory, large linear system solvers, as well as geodesy. And so that group of experts is fairly small within the community right now. Again, I already mentioned the computation and storage needs at level 2. And then, one thing that we are always thinking about as we continue to fine tune our SDS architecture is to have the ability to process, reprocess a climate data record. We have now almost 20 years of mass change observations, really in an efficient manner, repeatedly for experiments. So many times when we run experiments to understand the impact of one choice or another, we will look at a 20-year data record when we reprocess everything, because that is important. Next slide, please. So thinking about accessibility, at what point do you consider data products open access? So we consider, as the previous speaker said, that actually we have been a very open community kind of from the beginning. All levels of data products are openly distributed, and methods and algorithms are transparent and communicated. Documentation is released for anyone that wants to reproduce that data processing. What are the project plans for growing applications? As Lucia mentioned, we have science team calls via Rose's science team calls. There's also many other calls, such as measures, that include Grace follow-on mass change data. It's worth noting that our European partners have been, that they have access to additional funding sources through special programs that have been very valuable to increase the utility of mass change data in the past. So the third bullet, how are we authenticating the user for producing a product? So the project typically would not promote a product from an individual user. As I said before, really anyone has the ability to create their own level 3 or level 4 data product from the level 2 data product that the project releases. in the past, we've actually found that having too many flavors of level 3 data products can be detrimental to having uptake by the community, and it causes confusion with new users. And so I think this is really an instance where less can be more. And this was something that was pointed out by a standing review board in the GRACE follow-on pre-formula or pre-launch going to launch, is that they were asking for really kind of a one standardized product that the project stands behind, because in the end there is only one estimate of Earth system mass change. So that is kind of where we have been going in the past, is towards finely tuned or curated, highly curated data products to then provide to the community, and then they can do their science and open it up from there. And that's why we have so many users at the level 3 and level 4 data product level, integrating with other Earth system observations to promote the Earth system science. So what are the criteria for an algorithm to be viable? So that's fairly straightforward for us. We have the ability to run 4 numerical simulations in a controlled closed environment. We can test the feasibility of algorithms. In real data processing, we use CalVal methods that we talked about earlier to help assess the viability of an algorithm. In terms of how we would support open science, the next bullet, the documentation of all algorithms to generate the level 1 through 3 data products will be made available, just as we have done in the past on GRACE and GRACE follow-on. We have open science team meetings, as Lucia mentioned. We have town halls at AGU, EGU, user workshops, et cetera, to engage with the broader community. And then the last bullet, how could a common framework to access another mission's algorithms amplify our project's objectives? We don't see a lot of overlap with other algorithms to develop level 1, level 2 data products from other Earth system observables. I think the mass change observations are fairly unique in how they're handled. So we don't see, at this point, it's kind of unclear benefits, let's say, of a common framework to access another mission's algorithms in a common ecosystem to make those level 1, level 2 data products. Having a common framework where a user can access level 3 and level 4 data sets from these ESOs and other missions has benefits that could extend to the project. For CalVal, kind of like we mentioned before, we rely on other geodetic observations for CalVal. And that's really where the synergistic Earth system science comes in. And that's where that could really be promoted at the level 3 and level 4 data set level. Next slide, please. Okay, and I think this is the last slide in this package. So constraints, barriers, recommendations. So, there is a constraint on the software. It's proprietary software to do the level 1 and level 2 processing. I think a barrier, if we want to call that, I kind of agree with what Lucia said about barriers. The paradigm for MC, what we always say is the satellite is the instrument. It's a suite of 4 observables, GPS positioning, intersatellite ranging, a very precise accelerometer, as well as attitude determination. We need all 4 of these working in tandem to build a mass change data product. And that processing requires an expert user with sophisticated knowledge of the entire spacecraft system and how it's behaving. So from our past experience, we think there's limited value in making the level 1 and level 2 data processing completely open. That target audience is very narrow. The benefit seems unclear, and most likely it's negligible. The value increases significantly, however, with the level 3 and level 4 data products. We said 78% of our users are going to that. And that's especially true when we view that in say a common ecosystem alongside with other observations. So most of the addressing Earth system science happens primarily at that level 3 and level 4 data product. A recommendation, just reiterating again that the expert skill is really needed for the data processing at the level 1 and level 2. It's not just a software science problem or a data science problem. And I think that's it for the science talk. And then I would now transition to go into a little more detail on the data processing. Oh, and while I'm on this, I want to acknowledge also, I think I forgot, so Felix Launder and Brian Loomis also contributed to this, and I know they're on the line, so perhaps they can also contribute to the discussion. So next slide. So a little bit of this is redundant, but we'll dive a little bit deeper. We are inheriting a data processing system that has successfully delivered 20 years of mass change observations. There's been over 5,000 publications from GRACE and GRACE follow-on data. So there's no doubt that the utility of the data, it's going out to the community and people are using it. What's indicated here is the Science Data Systems architecture for GRACE follow-on, where we have the 2 satellites on the upper right. That data is downloaded to the German Spacecraft Operations Center, or GSOC. So our German partners are responsible for mission operations. At that point, that raw data then flows to GFZ, JPL, and UTCSR. There's some housekeeping data that gets cataloged. JPL takes the lead on the level 1 data processing there in the middle. And then those level 1, and I'll mention GFZ as a backup level 1 processing center, so we want to make sure we have a backup. And then that level 1 data then flows to the other SDS centers, both Goddard, who's actually not pictured here, but they should be. So Goddard, CSR, and GFZ, and then that's where the level 2 processing happens. And then, level 3 processing again can happen really anywhere. JPL has had the lead on that, where they do level 3 processing of every center's level 2 gravity fields, and then those get released, through PODAC. And they're archived actually on both sides of the Atlantic in German archive, as well as on the US side at PODAC, and that's where users access the data. Next slide, please. A few notes on algorithms, computing infrastructure, and external organization. So algorithms, it's important to have unique algorithms that are founded on the same fundamental principles for the level 2 processing centers. I mentioned this before, each center has their own code. There are a couple of different ways from which you can derive mass change observations. You talk about different integrators and things like this. And so that diversity is a strength, and it is a form of CalVal for the mission. So that is a good thing. The computing and storage, this could be a common ecosystem between the level 2 processing centers. In the past, each center has been responsible for their own computing and storage environment, and they handle that differently. It's unclear that there's a benefit to really having one central repository for each level 2 processing center, but that could, of course, be considered. For the infrastructure, heritage, the processing centers usually rely heavily on local compute nodes. There has been some more recent movement towards shared supercomputing systems, especially for more experiments that aren't time sensitive, let's say. In the past, we have looked at, say, relying on Amazon Cloud and doing kind of on-demand computing and paying per compute hour. Since the computing cost or CPU time is so much, in the past that has been an unaffordable solution for the project. And so that has driven past decisions to go more towards local computing solutions because they're more affordable. And then external organizations, nothing to say on that. We don't actually have firmed up partnerships yet for MC. Next page, please. So our current implementation plan, again, we inherit 20 years of very successful SDS capabilities. This relies on software that has been developed, starting in really the 60s and 70s, that have been independently owned by each processing center. In lieu of the source code for GRACE follow-on, an ATBD was released that provides the algorithms necessary for a user to write their own code if they desire. The project schedule, we don't have a detailed schedule like was shown before, but pre-launch, we We do have the ability to and do numerical simulations to verify requirements are met. I will show you an example of that at the end of my talk. And then post-launch, the first data release will have a very high level of maturity. And I really, the point that we've been doing this for so long, a great example is that our very first Grace follow-on data release, the quality of those fields was on par with where it took us 15 years to get to with Grace data processing. So we've learned a lot, we continue to learn, and all of those lessons learned will be carried forward into MC, and we expect our first data release to have a very high level of data quality. Next slide, please. Okay, so do we share any data or algorithms with other ESOs? Not that we are aware of, no. Our primary aspect of integration with the other ESOs, again, is kind of at the level 3 gridded products or through data assimilation systems when we view these observations in a common ecosystem to address Earth system science questions. Are there barriers to enabling collaboration? So, it's really, I think it's unclear that there are advantages to having the collaboration within the data processing system at the level 1 and level 2 level, rather than forming the collaboration kind of outside that core SDS and having that really centered around the level 3 and level 4 data products. That's a good place to enable the collaboration. What are the opportunities for improved support of Earth system science? So yeah, this is a good one. So one area where we continue to push and can improve upon is providing very robust estimates of uncertainty on our level 2 and level 3 data products. Those can then go into data assimilation systems and improve how the mass change observations are assimilated more broadly. We don't currently neglect it, but we have some room to run there. And the reason it's not a solved problem is because it is a challenge. Harmonizing, the second bullet there, harmonizing MC observations with other remote sensing observations is also a place where the community has been pushing. So looking at them in concert with Earth surface deformation, NISAR SDC or GNSS observations or altimetry observations. There's a lot of room there for synergistic Earth system science, and then just comparisons of other data sets, and actually combination of data sets can yield insights into the Earth system, as we're finding. Next slide, please. Okay, supporting open science. So what is this definition of open science mean in the context of data processing systems? Really to provide an open collaborative culture where we're trying to expand the uptake of MC data and accelerate scientific research and understanding. Again, we see that entry point kind of at the level 3 and level 4 data product level. That's where 77% of our downloads have been from the users. And that's really where the project has pushed over the last 20 years, because that's what the user community was telling us, was that the level 2 fields are not really what they need. They need something much easier to handle and ingest to answer the science questions that they're after. And we see that now that we've matured the system. So what do you feel are the most beneficial opportunities for improving MDPS to support the open science? So this is an area where we could have, again, maybe more expanded uptake of the data. I think increasing access to kind of an instant creation of on-demand mass change time series with robust uncertainty information. That is something that we could really push for, and we probably have all the pieces in place to do that. But that really drops barriers even more, so anyone can just with a click of a mouse or an upload of a shape file, get a mass change time series for wherever they want on the Earth with uncertainty information. Thank you. I think this is my last slide almost. What are the barriers to supporting open science? So again, the code was proprietary for level 1 and level 2 processing. We don't believe there's a big return on investment with making those open, and we really haven't had requests from this code from users in the past. And then what components will be developed in the open? So really we have a heritage system that largely relies on proprietary software with open algorithm specification for replication when desired. Next slide, please. Okay, pain points. I already mentioned this kind of, we have a 20-year climate data record that we need to process. Also, the expertise required is high. What does system efficiency mean? Cost-effective computing is important. The data processing does require significant compute time. And to the extent that we can, automation to reduce the need for human intervention. We've kind of been pushing there, but there are places where we need human eyes on things to make sure that they're going correctly. And then, is there anything else that we want to share? I think just to reiterate that we have a really mature data processing system that's been finely tuned over the last 20 years, and our plan is to leverage and build upon these systems. Next slide. Maybe go one more slide. I'll just show this as an illustrative. This is a flow chart of what was used in GRACE follow-on pre-launch to verify the flight requirements were met, from generating raw, level 0 to level 1 to level 2 data. And obviously this is an eye chart, no one can read it, but it's just shown to illustrate the complexity of the code and all of the pieces that interact with each other to make a final mass change field. Okay, that's all. I'll stop.
Thanks. So now we have 10 minutes for questions from the working group. Elias?
Sorry, I was double muted. Yep, here's our first question for you, David. It sounds like the plan for MC is really to bring, you have a legacy system, you're going to bring in data from other previous things that you've already done, and as MC collects data, the algorithms and things will be there, and the processing system will be a legacy system. What pain points would you say that that MC is envisioning that this study will help them solve?
That's a good question. Maybe I would. So I do think that there is opportunity for kind of in a, I'll say, a shared ecosystem of accessing other geophysical observables to kind of view mass change concurrently. And there's some examples of that exist, but that could probably be improved. But yeah, it's a good question. I don't know, Lucia, do you want to answer anything to that?
Yeah, I think I've mentioned that I like, I see our users having difficulty combining data sets. At this point, I only have one member of the science team that happens to be in the NISAR science team, also involved. But this is really a great area of a science team kind of work for people getting together NISAR data, for example, or any SAR data with GRACE, or GPS data with GRACE. Again, the NSIDC data sets, for example, looking at ISAT or other data sets, bringing that science together. So for me, a vision for the future system would be for people who come from the outside to easily get the connection between the different DACs. Now it seems like the people need to know ahead of time where to go looking for different things, as opposed to any one of our systems presenting them with the opportunity. If that makes sense to you guys, I'm not designing the system, but that's what I would like to see, because I see people struggling with writing proposals to do that, even though they know the idea. They just can't get the workflow together to propose it.
I think, yeah, from the way that some of the slides maybe were presented, at least I got the impression that there wasn't much need to share data or look at other data from the other ESO missions, but it sounds like that is definitely one of the things that MC would like to do. Obviously, the access point from the DAC is outside the scope of this study, right? This study is scoped within the mission data processing system, but there's definitely things that happen within the data processing system that would enable those data to be used much simpler in the processes that the mission itself needs, right, for calibration and, you know, UQ as was mentioned here. Okay, thank you for that. Hook, you had the next question.
Yeah, actually, it was about the point that was raised about mass changes, potentially proprietary or close source level 1, level 2 algorithms. I was just curious, is there any general guidance? Maybe this is a Kevin question. I know he commented on the WebEx chat there, but just more so about what about follow-on activities in terms of transitioning from proprietary, you know, software to, or at least to open sourcing some of these things. I mainly ask because we do hear that others in other missions, like some of the SBG algorithm community folks, they have been forward thinking in some of the historically proprietary radiative transfer and atmospheric correction code. There are efforts in developing open source alternatives already to kind of mitigate this ahead of time. But I was just curious, are there any thoughts on this on the mass change side and plans for, you know, any alternatives?
In alternatives to the proprietary code?
Right, or at least just addressing some of the comments about, you know, the principles behind open source science.
Well, I think a lot of our thinking, and I think Lucia mentioned this, is that I mean, there's only a handful of centers that have that do the level 2 data processing, and in the end, when we converge to the same solution, that tells us something good. So it's in terms of value added. I think that's a question: is does it add value? And I think that's kind of unclear. But again, we openly share the algorithms, so anyone can you know, architect that code. I think the history behind it even being closed is that it used to be ITAR regulated. I mean, you can navigate missiles with it. So we have a challenge bringing foreign postdocs in and having them have access to the code. So the idea of opening things up broadly to anyone, we have challenges just internally at JPL, having JPL employees having access to it. So I think that's a challenge.
This is Kevin. Maybe I'll just chime in here with some thoughts. You know, we've historically seen kind of the reluctance to make things open, and you know, I think it's always hard when you have something that you know and you've trusted and you've used before. So that I guess isn't all that surprising. And we have seen some pretty darn good examples of people kind of leaning forward in this area where things used to be closed and have since become open. And I think you heard a lot about that in actually the NISAR discussion. Their core software systems, you know, when we started the Griffin project a long time ago, were not open. And we went through the very laborious and arduous task of not me, but JPL did to move those things open, including addressing things like EAR 99 and so on and so forth. So, you know, I think now's the right time to have that discussion. And, you know, even if things are really complex, you know, I think for kind of the aspects related to trust and reproducibility, you really need to see what can be done in those areas to make those capabilities open. The core software.
Kevin, the question is the purpose of it. Is it really worth the effort for this project to go into distributing that level of a code? I mean, I'm just thinking of it from the science team perspective. Who will be the people, and from the proposals that we get, right? Who will be the people who could potentially make use of that, and what would the outcome be, and what is the best use of their time? we're looking for people to advance things, not to reproduce what is done in the past. Maybe, it is an issue of balance in my mind, more so than anything else. I want people to move on, and I would be worried about unvalidated data sets. So who has the responsibility if, say, somebody gets the code for some reason, the alias incorrectly because they put in the wrong parameter? I'm just sort of hypothetically saying there is a group that comes up with some result that shows a contrary result. Who is really the liable entity for the core data set? And I think as it is, we bear some responsibility, especially because this is a critical data set for mass balance and climate, and we bear some responsibility if somebody shows that they see some trend that is an artifact of the data set. For example, I would feel that NASA needs to investigate that because it's a NASA authorized data set and it's part of our standard products. If somebody else does that, I wouldn't know how to approach that. So I guess you have to maybe, and this is what I was referring to, that sort of a demo project to kind of walk through the steps to see what is the gain and how do we implement it? Because if we have limited resources, I want people to be able to get into a data fusion with these other ESO missions, because this is where really we want to see the biggest benefit, rather than retraining hydrologists to smooth gravity fields when the geodesists have been doing it pretty well so far. Thank you very much. I don't know. I think these are the questions. I'm not saying that I have the answers, but I think you need to think about these things when you're coming up with these solutions ahead of time. And this is why I think we're presenting this information to all of you to consider it, because it is important where you're going to choose to make the investment that you're going to make, and you make a difference. But that's from our side, it looks that way.
So yeah, I agree. Like making the tough decisions on the investments is a big question, and how do you get the best value out of those investments is another question.
Yeah, I can give you another example on this.
Well, let me just kind of finish my thought real quick.
Sorry.
And I think if you if you go back to the original open data policies, I think people could have made similar arguments like, hey, why do we need to make all of this open? Certainly USGS and ESA did that for a long time, right? And others did it too, right? And you see it over and over again, but you don't really know the true value of being open until you actually are open and you see the type of demand that people want. I'd say too that it's not dissimilar, like the usage patterns that you recognized here with higher level products being used more often than others. But that's not to say that they're that you've gotten all the ideas from all the people. I understand that this is very complex, and I'm not that.
Yeah, I get it, and I'm not advocating we shouldn't provide people the code. I guess what we're doing in measures, I just don't. I feel reluctant to say every project that's funded under measures that is giving over their code, they also should be held responsible for life to support that code.
Oh, absolutely not. Yeah, absolutely.
So this is that. So, okay, so if you map that to a level 2 product, then where is the liability? Even if, one of these packages actually, like the geodyne package that is the, orbital dynamics, that is a core package of that nature. Goddard does give it out to universities for students for training. How do they responsibly use it? Goddard being civil servants, they actually do support it to some extent. But there is a limit to how much you can support that. And then this is where then, if you can't support the code, who's responsible for the outcome that a group gets by using that code? That is the big question in my mind, because yeah, I am absolutely certain you know, proprietary things aside, maybe we can work this out. Exactly what should we invest in that effort if we don't expect some kind of a return?
Sure. So
that is the only thing I want to.
I fully agree. I see what you're saying.
I don't see the return. That's why I'm not jumping
I
at
think
this.
I think you've raised a number of items that hopefully the study team can look at related to long-term maintenance of algorithms and software. And we certainly don't have all of the right answers for that now. I think in Katie Baines' slides, she kind of put forth that maybe that responsibility should be in these kind of evolved DACs, these science enabling centers, for long-term maintenance of the software, in close collaboration with science team members and that type of thing. But I think that's still TBD, right? Like exactly how we do that's a big question. I think the other question though about like how do we, and I've heard this a couple times during this workshop, is like how do we prevent people from misusing our products? We can't. I mean, that's basically where we get to. Every time we do anything, even the validated products, people misuse those all the time. They don't use the quality bits. They don't, read the documentation. They don't, do all sorts of things, including people like Google Earth Engine, right? And our job is to see that and to go out there and help them correct it, to educate them. I think this is a constant conversation we have to have, but it's worth it because when we open it, we allow people to really trust it. If they can't understand it, well, that's their fault. They got to go do the hard work to become smart enough to do it. That this isn't saying that everything that we do should be, super easy. It's not like ordering an Amazon package or something. You got to put in the effort to do the work. But I think that we have to put in the effort to allow people to engage if they so are want to. And I think that helps us ultimately scale out who can participate beyond those groups that only have access to facilities or what have you, that you need to do it. But that's a philosophical thing. Maybe the study team doesn't need to deal with that one.
It's also a little legal thing, and I just mentioned this briefly. The Data Quality Act, it's something that USDCRP was grappling with when we started. I think it was assessment 3 or 4. I don't remember, the climate assessment, national climate assessment. And luckily, only one agency took it on to deal with, and I think it went to the NOAA lawyers. So we escaped that at the time, but it was a very complicated thing, and I would recommend that somebody from your team actually looks into that. The Data Quality Act binds the government to a lot of things for data we distribute.
Yeah, and there's nothing saying that we would distribute anybody's product, right?
Okay, but it's just something to look at. Yeah.
And I think that there are actually a number of acts and executive orders related to all of this, which are sometimes in conflict, as is often within the government, right? So we have the Open Data Act, we have the Geospatial Data Act, we have the Evidence-Based Decision Making Act, we've got, as you said, the Scientific Quality Act. We have a number of executive orders related to this. And we'll probably see more. And sometimes, they are in direct conflict with one another. So, it's difficult to do. I think Steve Crawford has done a really good job at putting all of that together in SPD 41, and making at least, an attempt at saying, hey, these are the current guidelines we all are supposed to follow. We'll definitely take a look again at the data quality component. But I mean, when it comes to standard products from missions, NASA is going to have a product or products from those missions that we put our stamp on that will be the NASA products or the NASA Plus partner products. And those will be the official products. We're not making any suggestion, and if it came across that way, I'm sure we didn't mean it, but we're not making any suggestion that NASA is going to take away, that NASA is going to relax that responsibility on ourselves. We are going to do that. That's what we're going to do. But if people want to create additional products or come up with different methods using any of the data that we have, that should be highly encouraged, because we certainly don't have enough money to fund everybody that has a good idea, right? Mm-hmm. So we've got to pick the best people, the people that we think are the best. But there could be some really good ideas out there that didn't review well. And maybe they have money through a foundation or a partnership or a commercial enterprise, and they can build off this. I mean, I think I might have blown up the schedule. Sorry.
Sorry. My bad.
Can I ask a related question? Is like making the code, so let's say completely open, or even the algorithms, I see some in the chat, who provides the support to users?
So
is that the responsibility of the project? Because that really, when I think about this, that would divert significant resources, from improving data products, because there's such a small few people that have the ability to process, to basically being like a software support center.
Yeah, and that's a great question, and I think the answer there is that we can rely on DACs, or these things that we were referring to as science enabling centers, to work closely with the projects to make sure that they can provide like the first and second level of support for that software. I think that is an incredibly important question. They're not going to know all the pieces of the software. They're not going to be able to do every single thing, of course. But for the mundane questions, for the people that are maybe haven't done enough homework, hopefully they can answer their questions as we work together much earlier in the mission lifecycle, right? So part of the reason of starting these conversations between DACs and missions in phase B, and I think Michelle earlier or yesterday was saying maybe we should do it even earlier, is so that you can begin to rely on them to answer and alleviate some of those types of questions, right? To provide that support. I know it takes a little bit to train them too. There's no doubt about that, but we would provide them with the capabilities just like we do today to answer questions. Does that answer your question? I'm not sure.
It does, yes.
Okay.
Not well, but it does.
I think it would be a very big challenge for that to actually be executed. But I understand the philosophy.
Yeah, and
well, at some point too, like missions end, right? And right now, what we do when we close a mission down is in phase F, the final reprocessing happens, and then all the artifacts for the mission get pushed to a DAC, right? Including all the software and everything else. And it kind of runs into Lukia's problem again, which is like, oh, great. We just closed down this project, but maybe we want to go and continue doing processing for similar types of data. How do we do that? Who maintains that legacy, right? After we're dead or after we leave? And I think that we have to keep that mindset open as well, right? We might have to do some training to make that work, but I think it's worthwhile training.
Yeah, it's just that for this mission, and maybe we need to grow more people and clone some of the groups, but I'm telling you, because I'm connected with all these people, I have the same group of people that have multiple tasks between, like David or other people at UT, that haven't been able, because they're occupied, to make the Grace follow-on mission work. They can't finish off the reprocessing of Grace, and they're moving on to their science team project, and then they haven't done their measures project work. So it is kind of the same group of people that are basically squeezed from all directions. You know, I see that because I happen to be involved in all of this together with them. Had I not been working in all these programs, I wouldn't know. But you know, it is a limited group of people. For me to say, oh, great, have these people now teach your new science center how to train people using the level 1 processing code. It's just really very far from what we should be doing, but because of that reason fundamentally. But anyway, I think we
Yeah, I got it.
communicated that point well.
All right, let's hand it back to the folks.
Okay, are we ready to get started again? Dave Schimmel, are you ready?
I'm ready.
Awesome. Let's see if we can get your slides up.
That's right. I'm ready. Are you ready?
There's your slides.
All righty. Thank you. Let's go to the first slide. I'm going to give a brief introduction to SBG, and I'm going to discuss how the particular science applications and characteristics of the mission interface with the open science conversation. SBG has a very broad agenda. It actually has most and very important decadal survey objectives and applications in all 5 of the science focus areas. And the mission was defined with quite a bit of detail, maybe almost too much detail in the decadal survey. Let's go to the next slide. So this is what the NASA mission looks like. 2 platforms, 2 instruments, or 2.5 instruments. One in a morning orbit to minimize cloud cover, the other, the thermal instrument, in an afternoon orbit to maximize thermal contrast. They're both very wide swath instruments. The total data downlink from the 2 platforms is somewhere between 1/2 and 9/10 of a NISAR. So it's big by our current standards. And we're provisionally calling the 2 platforms heat for the thermal and light for the VSWR. Those aren't final, but you'll see them on the slides. If we could go to the next slide, please. One of the real pressures from our science community is on revisit. The value of the information appears to increase quite dramatically the more frequently it's obtained in order to observe rapidly changing land surface temperatures, in order to observe rapidly changing phenomena in the coastal ocean and inland waters, and to observe rapid changes to vegetation, as well as a wide variety of applications, landslides, wildfires, oil spills, where the application would benefit dramatically from a rapid cadence of observations. We anticipate that SBG will be on orbit with a number of other international missions. And we've included data harmonization with these missions in the spirit of Landsat and Sentinel in many of our operational concepts. And we're actually very interested in the possibility of ingesting international data, at least for certain regions, either routinely like irrigated agriculture or on demand like volcanoes, into a harmonized data stream for the community. Next slide, please. SBG enables a very wide range of science and data products. I've captured some of the decadal survey questions and objectives in the blue, green, red, and other colored boxes here. The gold boxes show some of the core, we call them level 2+ data products that we anticipate producing. On the bottom, you see SPG's role in monitoring the land and coastal and inland water surfaces, looking at biological phenomena, hydrological phenomena, in water biology, and the solid earth. But SPG also enables a number of connections between the Earth's surface and the global Earth system, including volcanic emissions, methane point sources, feedbacks through temperature, albedo, and evapotranspiration. And as such, if we can go to the next slide, it's very synergistic in the ESO. And the SPG community has really embraced this. And we've actually identified a number of science issues where the ESO synergism will really be the main event instead of a sideshow. We already saw one example. I was really pleased in the very, very first presentation in that the synergism of the ESO missions will enable a comprehensive look at the water cycle, including the retrievals that NISAR does, for example, for wetlands, the total water storage from mass change, aerosols and precipitation from AOS, and from SPG, evapotranspiration and snow hydrology. We also see synergism with the program of record, and in particular, Glimmer and PACE, as enabling a view of the water cycle and aquatic biogeochemistry from, as we say, the mountains, the headwaters, through the rivers, into the coastal ocean, and ultimately into the open ocean. So the idea of a common layer across a number of NASA missions is very, very exciting for the SPG community. And so we've been embracing this new initiative quite enthusiastically, albeit, and you'll hear this from my colleagues, with a certain amount of trepidation. Next slide, please. So international collaboration is really central to our concept to address revisit. And this is just to illustrate our anticipated partners, ESA's hyperspectral CHIME mission, the CNES, ISRO, Trishna mission, ESA's land surface temperature mission, LSTM, and also ingesting in situ cal-val data from what will inherently be a global network of collaborating sites. Next slide, please. So SPG and Open Science, I took this photograph at the Whole Foods nearby. Like Whole Foods, we're committed to traceability and transparency. We're very much focused on the data policy and the spirit behind it. We're actually actively in our Pathfinder activities moving away from legacy proprietary codes. That's very, very painful with ModTran. And we're using open source code repositories, similar to what I've heard from a number of my colleagues. We're using Jupyter Notebooks. We have a GitHub, and we're doing everything to avoid having an open source regulatory issue at the end as a roadblock. We're opening things up along the way as we can. We are partnering with an AIST project to develop an environment for easy user supplied algorithm execution. And as I'll show you in a few slides, the high number of potential products really dictates an innovative SDS solution. Next slide, please. So SPG has 10 core product suites. They're shown on the right that map onto the science areas for the missions. Some of them support, like evapotranspiration, multiple science focus areas. Many of them are independent in that they're produced either from thermal or V-source spectroscopy. But there are a number of product areas that either have an element from each. For example, some minerals are best retrieved in the V-SWIR, while others appear in the thermal. Some actually require combination across wavelengths, and a few can be retrieved redundantly, for example, carbon dioxide point sources in both regions. However, if we go to the next slide, we did a user survey, and the SPG algorithm working group identified nearly 200 potential products. So the upper table shows the list of potential snow products. We're planning on producing just a subset of them. The lower shows the list of geology potential products and subproducts. Again, we're planning on producing only a small subset of these. And so with 10 research and application areas identified in this assessment, it's actually published in Remote Sensing of the Environment, we come up with nearly 200 potential products. And I think that this is really key. I can't even imagine, after a number of years of Rose's opportunities, that NASA will even fund all of these. Some of them, for example, in geology are applications and data products that have been developed and are used in the mineral exploration industry. They're not likely to be research algorithms at all. So the idea of an environment that makes it easy for users to take their code to the data, assuming they're willing to adhere to open source policies, is very, very attractive to us. Next slide, please. What are some of the drivers? So SPG is an applications heavy mission. We have a large and diverse applications community with well over 100 people already participating in our applications working group. And as has been said for some of the other mission areas, most of our participants don't have the skills or the tools to work even with a level 2+ data product, but really require application ready data, ARD. And this came out very, very clearly in the assessment that our RTI contractor did. Low latency is critical for many applications. Again, in two different ways. Some applications require regular low latency data. For example, water management in agriculture requires evapotranspiration as frequently as possible, whereas others require low latency to capture episodic but important events like volcanoes or wildfires. And ease of access, almost an environmental or a science justice issue, ease of access is going to be critical for users who are not traditionally involved in the global technical geospatial community. And you know, we often look at how simple can products be to access. A few folks have mentioned that users want a spreadsheet. In our community, they tend to want something that can just very seamlessly go into a geographic information system. Next slide, please. Data harmonization, data fusion, and partnerships. So the notional concept for SPG achieves only 30 to 50% of the desired revisit from the decadal survey. And so again, the international collaboration can lead to actually achieving very ambitious targets, but it will require cross-calibration, harmonization, reconciliation of a number of issues that occur in blending data. And for some of the applications that would require rapid ingest of partner data, um, uh, at least some level of immediate cross-calibration, and potentially fusion to common time-space grids. And I note that even higher revisit or downscaling could probably be achieved by fusion with Landsat, Sentinel, or potential commercial opportunities. And there's huge interest in this in the science and the applications community. Next slide, please. Similarly, many of the science questions that come up for the SPG community, researchers are clearly going to take advantage of the entire ESO. I mentioned the water cycle with AOS. There's tremendous interest in interactions in the boundary layer with the surface energy and water exchange. Mountains to the sea, the transport of water, minerals, nutrients, organic matter from source regions to the ocean is a motivating science challenge for the SPG community. We would undoubtedly benefit from the maximum amount of interoperability and relatively easy reconciliation of differences in time and space discretization, which really requires data fusion to be easy in the ESO context. The research and applications would clearly benefit from a common high-level science data system capability, particularly if it were also interoperable with our international collaborators. Next slide, please. Schedule, schedule, schedule. Some of these imperatives are sufficient that the SPG team will build these capabilities, will find partners to implement these capabilities, or will work with anyone who's interested, for example, the value-added commercial sector, to provide them. But a number of decisions have to be made on a relatively tight timeline. And it would be very, very valuable, and I think Ben Phillips will speak to this, to get a sense of what might happen and when with some of these open source capabilities. You know, can we join forces to provide some degree of common agreement around early core and essential capabilities, so that we can build that into the planning, the development of requirements, and the design of the mission-specific components of the science data system, but also to avoid looking for additional resources to develop capabilities that might be better developed jointly across the ESO. Next slide, please. Current status and needs. And I really want to frame this sort of as pain points or pleasure points. The SPG team has embraced open science, and we've immediately implemented some early open science measures in our pathfinders. And from that, we're getting a sense, a growing sense of what the advanced and innovative open science capabilities might be. This notion of an algorithm sandbox would have really direct benefits. Being able to support literally hundreds of science and application users who want to produce custom on-demand or bespoke data products, but potentially with quite large volumes, is really challenging to envision in a traditional SDS to DAC model. And because of the high level of synergism between the missions, we'd really benefit from a layer where the ESO data are available and relatively early, easy to be interoperable. Finally, I want to make the point that a number of my colleagues have made, that to really grow the size of our user communities, to address the most diverse range of user communities and applications, really requires level 3 and higher level data products. We anticipate probably exponential growth in the number of users as we move from low level 2 reflectance products to level 2+ products like plant functional traits or colored dissolved organic matter in the water column, to even higher level data products that might be used for mineral exploration, conservation, or land surface interactions with the atmosphere. So I think that's my last slide, Sarah. And I want to wrap up there and leave plenty of time for my colleagues to speak.
Thanks so much. So Jeff Pon, you're next.
Great. So I'm Jeff Pon. I'll be briefing the mission data processing system for SPG. Next slide, please. So here's a current overview. So for SPG, we're currently in the pre-phase A life cycle. So the mission concept is still in formulation, or pre-formulation, in fact. So a lot of the open science use cases needs are evolving and are all, of course, subject to change. However, the briefing today, on at least for the mission data processing session, is to give the system architecture working group an idea of what the current architecture is starting to look like to help flesh out some of the open science goals and see what kind of capabilities could be leveraged in the spirit of open science. Just one thing I want to know that that this material brief today should not be interpreted as anything final. We are in our pre-phase A life cycle. So next slide, please. So as Dave mentioned, we basically have 3 different components for SPG. We have the SPG Heat spacecraft hosting a TIR and VNIR sensor, an SPG Light spacecraft hosting a V-square spectrometer, and then the third leg is actually also the Constellation Pathfinder, which the details of that are still in formulation, but the intent of that was to host some sort of small sat constellation hosting several other perhaps spectral sensors. Next slide. In terms of the architecture, on the left, we have our inputs. We have basically the V-squared, TIR, VNIR, and the Constellation Pathfinder wideband data. This is all the instrument broad data that'll be going inside our SDS system. In addition, there's a bunch of ancillary data we're receiving, and also external data providers providing like mineralogical data. Those inputs will be cataloged and then been processed into various products up to level 2 reflectance and level 2A cover types. And then there's a slew of other products still under definition that Dave mentioned. Those were all those 10 core products and also 200+ products that Dave mentioned. All that is still under definition. And then one thing to note is some of these products may also be provided by our international partners. We're partnering up with the Italian Space Agency, OSI. So they may be providing some additional products, specifically maybe perhaps the VNIR data. Of course, that's still under discussion with our international partners. In addition, there's also another component on the bottom right. We have AIMS has also been discussed to be providing some data products using their on-prem high-end computing systems. So that's also still under definition as well. In addition, we also could support hosting a instrument cal tools within SDS. Previous missions have provided an environment for the project to host the instrument cal tools. It's still unclear yet whether the instrument team for SPG would want to utilize this capability, but that has been provided on previous missions. In addition, there's also a algorithm development and validation environment that has also been provided on previous missions. We're looking to utilize this to do the internal development, but also potentially open this up for public access if we can figure out all the policy hurdles and develop the necessary platforms to do that. Go to the next slide. Okay, so here's a little more in-depth view. On the left, you'll see the various different ground station components that we'll be receiving data from the 3 different spacecraft legs. That will all be brought into some sort of centralized cloud service. And then we will be developing apps or PGEs to process that data up to level 2 or level 2A and store those products and distribute it to the DACs and the general community. As previously mentioned, we also have international contributions, so perhaps Aussie will be providing their potential VNear data products over to the JPL SDS, and to enable that sensor data fusion with the tier sensor data that JPL will be providing, and then provide that out to the DACs. Similarly with AIMS as well, they will likely be doing the same. And the critical point is, for those sensor fused data products, we do need the data to be co-located somehow. And as mentioned on day one, getting involvement with the DACs and SDS would be certainly beneficial, as perhaps we need to rethink where certain processing is done, certainly for those sensor data fused products. The data definitely does need to be co-located, and because these data sets are so large, we do want to avoid extra transfer hops or duplication of data. So that's something that's still to be considered. As we're developing these PGEs, there's an environment that that previous missions have used, like NISAR. They provide an algorithm analysis environment utilizing Jupyter notebooks that could be deployed as document containers. So it could be quickly scaled and deployed. We're looking to do this as well. However, as been previously mentioned, this historically be limited to the project access. But if there's ways that we could potentially expand the concept to open to the public, we're certainly interested in doing that if the policy security and all the cost barriers can be addressed. And we're hopefully looking towards this open science working group to help resolve some of those questions. Good, on the next slide. Okay, in terms of data sharing or algorithms for SPG or the mission data processing, where the missions listed there are all several spectral missions that we're utilizing surrogate data for. And in terms of algorithms, as Dave mentioned, a lot of the algorithms were derived from previous missions that were already open source. So we're utilizing a lot of the other ESO heritage missions and leveraging their existing open source and looking towards developing new algorithms towards open source as well. In terms of barriers, I think we have a lot of the same barriers that other projects have mentioned. However, I guess one unique barrier that SPG is facing is we are in our pre-phase A, so determining whether the science mission goals and the open science goals can all fit within our schedule and cost box is a bit difficult at the moment, since we haven't actually defined the schedule or cost box yet. So as we define and mature the mission concepts, we'll have to keep in mind the open science goals and try to fit everything within the box, basically. And another barrier that we face, and also other projects face, is just ensuring or determining which funding sources or open science capability providers, who's providing what. There's certain things that the projects can bring to bear, but there's also other project agnostic funding sources or initiatives. And just determining who's going to be providing what is sometimes a challenge. And then, as other projects have mentioned, we also have security issues. We're no different. We have international partners that we need to interface with, and when building an open science platform, we need to make sure they have access as well. But also, if we're opening up to the public, we have to make sure we're adhering to all the cybersecurity concerns to make sure the system is open, but at the same time protecting against malicious actors. And similarly with ITAR as well, we also have to adhere to the same ITAR constraints as other projects. In terms of opportunities for improved Earth system science, so one blessing is SPG is early on its life cycle phase, so there's potential we could leverage those new open science capabilities as they become available. However, as we understand, a lot of these platforms are still in development. So in terms of schedule, the schedule may not necessarily align, in which case we would have to go SPG has to go forward with some sort of point designs to make sure our development schedule isn't delayed, and also to attempt to provide certain capabilities that maybe aren't provided through those project agnostic initiatives. But as SPG project continues to mature and over its life cycle, we continue to evaluate over time what capabilities exist and adjust our plans accordingly to try to incorporate more open science and more of those features and platforms while maintaining our schedule and cost constraints. Next slide, please. In terms of what does open science mean for the data product systems, I think basically in it basically boils down to kind of three different areas. It's really improving the public access and ease of use of basically the mission data processing system, which is being able to discover data, sharing it, and also processing the data, but also including the community algorithm contributions. In terms of what's most beneficial for opportunities for improvement, certainly ease of usability is definitely a big factor. As mentioned before, a lot of the scientific community, they're really focused on science. Then sometimes they struggle with a lot of the new cloud aspects, so they need help. But in addition, the SPG project has a lot of data. And the public's going to need help to be able to filter through that massive amount of data to figure out what data is of interest and also what data to process. So if there's ways we can help ease the community in terms of accessing and filtering that data, that would be very beneficial. In addition, implementing flexibility in the processing of that's requested by the public users to select different algorithms or processing knobs would be very beneficial, so that the end public user doesn't have to necessarily reinvent the wheel. This could save them a lot of headaches and pain to basically develop their own applications if they could utilize existing applications. If we have perhaps just tweak certain knobs, that'll cut down on a lot of the special needs of having a dedicated application. But at the same time, we also do want to allow for the ability for brand new applications, but perhaps providing these customized knobs could help reduce the burden of having to create specialized applications. And then basically also the one last thing that's fundamental is basically figuring out easing the logistical complexity of administrative billing, configuration management, and platform deployments. Basically all the mundane stuff that the scientific community will have to go through, but in order to utilize the open science platform, if we can make that easier on them, I think certainly this will be a much more successful initiative if we're able to allow the scientific community to focus more on the science than all the logistical hurdles. In terms of barriers, as kind of mentioned before, cost and schedule. SPG has its own cost and schedule timelines, which we would certainly prioritize certain open science goals over other ones. But basically every project has cost and schedule constraints, and basically we'll need to work around those. And then also the cultures and policies. Basically, we need to basically change the mindsets and the policies out there while addressing all the valid, cybersecurity concerns and ITAR rules. We'll need to figure out what are all the possible carrots that could be offered, and fortunately, what are some of the sticks that need to be implemented. In terms of the components of the data system that we'll be developing in the open. So as mentioned before, a lot of the components and algorithms are still under definition. However, a lot of the algorithms are being leveraged from existing ESO missions, which are already open source. And in addition, as mentioned before, that the JPL is only handling a core set of SPG products. There's a slew of other 200 plus products that Dave mentioned that we'll have to rely on the community to provide, because we simply just don't have the resources to develop everything ourselves. So that's a big important part that we'll have to rely on the community for that open sourcing of those products and of development of. In addition, we're also considering use of community-based Jupyter-based notebooks, just like our internal development of using Jupyter-based notebooks as perhaps a common standard. So we'll stay tuned to see how we can open that up to the public. And then, like other EOS missions, we're publishing this data to the DAC for public distribution. Next slide, please. Pain points. I think we've kind of talked about this already, but SVGs is pre-phase A concept, so everything is basically evolving. But we also have one other unique requirement or some pain points is that there's a subset of products within SVG that are time sensitive, and in order to meet the time sensitive science community's applications. So that's another thing that we have to work into our system and also be mindful of when building an open science platform. SVG is a hyperspectral mission, so there's a lot of data. So in addition, there's potentially a constellation Pathfinder being developed right now that may also exponentially add to the data volume by hosting a whole small sat constellation of spectral payloads. So data will be very large. So it's important to have system efficiency in terms of compute and storage. We want to one things we want to look into is reducing the waste of duplicating data and unnecessary transfer hops, especially with the scale of data we're talking about. And we also want to reduce unnecessary product generation, meaning perhaps there's different things we could build into the system to appropriately handle cloud cover areas or only processing certain products over certain geographical cover types. And then optimizing latency, prioritizing resources for those urgent response type of low latency needs, and then having more of a standardized product that's focused more perhaps on accuracy. So there's trade-offs on prioritizing resources and also perhaps using different algorithms for different needs. So one thing we're looking at is potentially producing a latency optimized algorithm versus perhaps a standard accuracy optimized product. So those are some things we're looking into. And I guess one last thing to share with the group is basically if there was platforms that could be developed to enable users the flexibility to, just be able to filter the data better and give them the knobs to process subsets of data. That would be, I think, reduce the burden on how much data products to be developed or produced. We want to serve as many people as possible, so trying to optimize the processing and the storage is going to be critical, especially when opening this up to the community, as demands on processing and storage systems could potentially balloon. So we got to be careful as we optimize and give the knobs to the users to basically do their best job as possible and help us help them. And so one last thing, I guess, in terms of developing the open science platform, I did witness a tech demo last Friday for ImageSpec. So they're doing an early Pathfinder for developing some of the open science platform, or rather developing a development environment that could be used potentially for open science for a platform. And they're developing some really interesting capabilities that potentially we can potentially leverage for SVG. However, that is just a tech demo right now. It's not fully deployed or deployed at scale. So we're monitoring their development closely. I think that is my last slide. Can you click fast? Next slide, please. Okay, and I'll hand it off now to Ben to talk about some high-level highlights.
Thanks, Jeff. Thanks, Jeff and Dave, for this great overview of the SPG mission and the community, the breadth of timeframes of data that this mission's going to produce. So I'm just going to re-emphasize a few of the key elements that were just raised, namely schedule alignment, partnership issues, and environmental justice, equity, diversity, and inclusion. So first, schedule. As Dave and Jeff both alluded, we should think about working on a plan to align the conception and implementation of open source science initiative timescales with the NASA mission project timescales. SPG is going to be defining most of its driving requirements in parallel with initial definition of this plan. The nominal schedule for SPG has this study continuing through the SPG NCR, and presumably there will still be elements of OSS design and implementation underway, even SPG SRR. So there's certainly a risk, that OSSS identifies, new directions that weren't foreseen by the project and require some reverse engineering to accommodate, or perhaps, doesn't realize capabilities that were anticipated early in the concept, study and project design. So this, potentially puts us in a position with new requirements that bring additional cost and schedule. So my first takeaway is, that we'll benefit from a more detailed schedule as soon as possible, and as we go along, that outlines when decisions are expected about OSS requirements and what capabilities or services the OSSs can provide for missions to leverage. So second, on partnerships, we know that partnerships enrich everything, and they also complicate everything. Dave highlighted the importance of international partners for SPG. In particular, there's the Aussie Thermal Partnership, and then this broad need for data fusion across multiple international missions to address revisit issues. And as other projects have also raised, this raises a number of potential challenges. Might the OSS requirements conflict with partner data guidelines? Will there be access or security issues in either direction? We know that we're going to have very large data volumes, and we'll be implementing cloud systems as part of the solution. Will there be compatibility issues there across NASA or preferred partner cloud platforms? So the quick takeaway number 2 is that we should really maintain an open dialogue from the missions on their partnering data dependencies, and from the OSS initiative, to cross-check that good intent and working to do the best thing for open science doesn't inadvertently preclude important partnering mechanisms and undermine some of those objectives, because we're going to be doing a lot of this in parallel, just in series. So third, environmental justice, equity, diversity, and inclusion. Dave mentioned the ease of access for non-traditional users. I want to emphasize that we don't know what we don't know about broadening access to new communities that we're not currently a part of or conversing with. So meeting these objectives is going to require identifying, including those communities from the beginning, asking them about their needs, as well as including them in the definition and implementation of new systems. There's been some good discussion about this in the workshop. The Applied Sciences group has a lot of good models, as Nancy discussed yesterday. The TOPS initiative sounds like a core part of this, so I really want to commend that effort, and I'm interested in how TOPS might help directly support the missions in effectively broadening participation by historically excluded communities, because these communities are many, and key community interfaces may also vary across different missions. So there's some specialization to optimize and have the greatest impacts there. So my takeaway 3 is that EJ, DEI, needs to be really collaborative across all fronts. It's in the OSS initiative through TOPS. It needs to be at the mission level through the diversity of the teams and their outreach and implementation approaches, and in our program implementation and management at headquarters. I think Kevin raised the question yesterday of whether, reaching into communities that we haven't reached into before, how far do we go in scope, and I think it's something that we really want to strive for. As Dave outlined with all the applications, ready data products, SPG has the potential to provide services in many communities, but to fully capitalize on that, we're going to have to make it a priority and direct resources in that direction. And I think that's an important consideration across the entirety of the ESO. So that's it.
Thanks, Ben. So really great presentations. What we're going to do now is 10 minutes for questions from the SAWG for the SPG, and then we'll do open discussion for the rest of the time.
That sounds good. Thank you, Sarah. Here's our first question. SPG, does it plan to share any data or algorithms with the other 3 ESO missions that were presented here today?
Elias, I'm not sure what you mean by that. The data and the algorithms will be open to anyone. There is a potential area of technical overlap with AOS in that the large platform for AOS is planned to include a UV visible spectrometer, which may have characteristics that overlap the SPG spectrometer. And we are in very close communication about sharing information about the atmosphere, which is, which for us is a bug, but for AOS is a feature.
Yeah, the question was sort of very much in line with that. Obviously, the way that SPG was presented, all the data and algorithms are sort of done much more in the open. So the question is, how do you plan to bring those data in and access those data that you need, for example, from AOS that may not be in that open, same way that you have yours? Is the plan to essentially just copy that data and bring it into the cloud or bring it into your SDS system? Is that the plan?
I think, Elias, to say that there's a plan for that would be jumping the gun. Right now, it's an issue, and there's not a plan to resolve it in place. The plan is to address those issues over time.
Okay. Maybe a follow-on question to that is the current thought process, and this might be more for the data system portion, to sort of have a rolling storage of data within the data processing and then have the rest of the data at the DAC because there's large volumes, or is all the data expected to be at the data systems control? What's the current thought process?
Yeah, under current estimates right now, we're assuming a rolling storage. The exact duration hasn't been defined yet, but we are expecting some rolling storage. So certainly if there's some archive data that has to be pulled, that could be problematic, obviously. And so certainly having those discussions with the SDS and the DAC, trying to delineate where process is going to occur is going to be critical, especially with those sensor fused products, especially if we start having sensor fused data with the AOS mission. That could be problematic because that means you have to somehow bring that AOS data over to wherever the SPG SDS is. And it's not clear yet whether they're in the same cloud environment yet. So those are all details that certainly still have to be worked out.
Okay. But as you saw earlier in the AOS portions, right, they're going to be within I don't think that their system is within the cloud, right? They're sort of an on-prem system. So that sharing is something you need to start planning for, thinking about how you would do. You also sort of mentioned a lot of, trying to reduce the...
Sorry, this is Robert.
Go ahead. Did you have a comment?
Yeah, I don't know how people got the impression we're not in the cloud because yes, the system that we're planning on building is in the cloud and the data will be in the cloud. So maybe I need to do some something happen when I communicate.
Yep. No. Yeah, I misspoke there. I confused MC with AOS.
Oh.
Yep. No. Sorry about that. You're absolutely right. Just sort of a follow-on for you, Jeff, in terms of, one of the things you mentioned as a pain points was trying to make sure that there isn't too much duplication of data. What's sort of the current thinking or the current plan to try and limit that duplication?
Well, within the SPG project, one thing we've been thinking about is because the data is coming from various different ground stations, like how do we get the data to one centralized location? One thing that we toyed with was perhaps just dumping the data to the nearest cloud provider to that ground station. We did some studies and found that that wasn't very cost efficient. It was better to just take all the data from wherever the ground station is located and pipe it over to the centralized cloud that our SDS will be processing the data. Just through some of the initial cost analysis we did, the duplicate of data and the transfer of the data was just, it didn't make sense. So at least that's within the SPG mission. Now, in terms of outside the SPG mission, that's something we need to work with other projects to resolve to figure out how to get their data, or rather, where are we going to process our data so that we can co-locate ourselves with those missions, perhaps. Or perhaps some of this processing moves to the DAC. I think those are all discussions that need to be had.
Yeah, and there was a lot of missions that you'd presented were sort of legacy missions that you might be using data with and incorporating with. Is that same kind of conversations happening in that same thought process for those data as well?
Yeah, so we are aware that some of the missions are already deployed in the cloud, so that's certainly influencing perhaps some of our decision making of maybe perhaps where we were considering to deploy the SPG SDS. However, we haven't finalized any decision yet on where we're deploying.
Okay. Here's one more question. In terms of the sort of software and developing software in the open, it seems like SBG has taken the approach that they'll do that from the beginning. What drove that decision, and what benefits do you see, or even hindrances from making that decision?
Yeah, Elias, I would say that it was driven by the nature of our algorithmic challenge. So we have 10 core products. Some of the algorithms produce multiple products. For example, one of the geology algorithms produces the abundances of a whole list of minerals. And the expertise to put the information together and the preliminary codes for those algorithms is coming from a very broad community. There are about 100 people on the algorithms working group. And so it just made sense to start that way.
Have you encountered any barriers to doing that, at least so far?
The major barrier is a broad community dependence on ModTran. Most folks using the licensed proprietary version of that code. That's been the biggest single barrier. The only other barrier is, the necessity to clear the code that's developed within the NASA centers through our administrative process. Other than that, it's been received enthusiastically, and it has greatly accelerated the pace of collaboration to have all of our algorithm code right now in several GitHub repositories, hopefully soon to be unified in a single one.
Sounds good. Here's one more question in terms of sort of the cybersecurity barriers that were mentioned, and it's not necessarily a question that was only raised by SPG here, but is that a you know, and maybe this is more of a general question for the larger set of folks here. Is that a problem that is being solved sort of by the missions themselves and their organizations? Is there a wait to see what NASA headquarters is going to do? What's sort of happening in that area of cybersecurity from your guys' viewpoint?
So here's my perspective. It's a total nightmare, Elias. We have challenges even sharing between JPL as an FFRDC and our NASA Civil Service partners. The administrative overhead of having to onboard people into JPL in order to share documents, those challenges are significant friction to collaboration. So the barriers that protect us actually are inhibitory even within NASA. Then when we begin, for example, we're doing a very open algorithm development activity that includes a lot of university collaborators and in some cases international collaborators. And there's very significant time and effort, staff support required to work those issues. And in a number of cases, there are no solutions currently, nor is it apparent that any solutions are being worked to be able to move things into more open environments. So I resonated very much with comments earlier in this long session. The administrative side of our cybersecurity and the paperwork or the electron work to work through it's a significant tax on people's time.
I'd say it's more than a tax. It's a impediment. It's a total roadblock for many.
Yeah, I agree with you, Paul. I couldn't agree more. And, you know, it seems like there are possibilities for secure environments that are open to validated users within a project, validated users across NASA centers. But as far as we know, those don't exist.
Elias, I may add something. I think Dave and Paul said it the best, but I think so far it's been a project effort to kind of maneuver itself around all those barriers. But I think now we're looking into some overall solution from headquarters to actually make this open source science happen.
Okay. In terms of maybe even, you know, an additional question to that, how should the SAWG take that into consideration, the fact that some of these barriers exist? Should we assume that some of these barriers will be worked through and broken down? Should we sort of take that in a different way and think about that architecture would have to be, the architecture would have to be fundamentally different because we can't get these barriers? Maybe some guidance on that to the SAWG would be helpful.
Well, we're not really the right people. We can tell you what the problems are, but these barriers are in place because of decisions that are taken by IT security at the highest level. And so I think this is something to discuss with Kevin, is what sort of structure would exist that would enable this. Right now, in all honesty, many of the desirable characteristics that have been discussed are basically shut down by the current administrative environment. I mean, on the project side, we're assuming that Kevin will solve these problems for us in some way, that there will be environments that have a different set of administrative requirements so that these barriers, these iron curtains that drop between various constituencies are not in place.
Hey, this is Kevin.
These cannot be addressed at the project level. They can
Yeah.
hardly be addressed at the center level.
I think that Dave, you make really good points. I think what we need to know, or maybe what the SAWG needs to know, are the characteristics specifically that we need for this to enable this type of collaboration. And you know, it's a lot easier to go in with a definitive set of needs or requirements for these types of environments than it is just a complaint that the process is okay. So what I encourage the SAWG to do is to make, you know, that part of their scope is to say, you know, if we want to, well, since we want to conduct open source science, what are the characteristics related to the processes to enable that? And I think that has to go into the architectural decisions as well. You know, it's probably a little harder, honestly, to do openness hundreds of times than it is, you know, a few times in terms of these environments, because we can really work with the CIO potentially to do that. But, you know, we won't design a solution here. What we need to know are the critical characteristics of such an environment.
One question that was asked of us that's sort of relevant here is this question of validating users. And right now, depending on the capability, a lot of user validation has to go on. For example, for us to give, within the SPG project, for us to give our NASA Center colleagues at Ames, Langley, and Goddard access to a JPL managed document store, we have to onboard them as JPL pseudo employees with an email address. That's really crazy that we have no way to share ITAR documents across centers without these sort of pseudo employment arrangements. We have a long list of things, even before we start opening to the broader community, where we have barriers within the project resulting from center decisions or NASA mandates about security. And I know we would all be very happy to provide you with a list of those pain points. Paul and I could make such a list in a heartbeat.
Well, you know, we can't even work with you on our Teams sites, so it's
exactly.
Oh.
Yeah, and I can definitely sympathize with those thought processes. So in terms of the SAWG, we'll take that as something that is a constraint that needs to be considered as part of the study and work through. And yeah, believe me, I feel your pain as well, just even getting all the SAWG members access to our Google Drive and Slack and so forth. So in terms of the goals of this study, just to revisit, we've got sort of 4 drivers, right? And those 4 drivers are that the architecture the architectures we're considering need to meet the mission's needs, should be promoting open science principles, and I think we've talked quite a bit about that. Enabling some data system efficiencies, we've even addressed that in terms of cost reduction, latencies, economies of scale. Sort of the 4th thing was support for Earth science system. For Earth science system, in the way that our early discussion, at least my understanding of what it was sort of constrained to these 4 missions that we're looking here. But from what I've seen in a lot of the slides and the folks that are presenting here, there seems to be the Earth system science is bigger. It's not just within these 4 ESO missions we're talking about, but larger missions and sort of across that. I wanted some guidance for the SAWG here. Should we be considering that 4th goal, which is supporting Earth system science, to be larger across NASA and maybe international missions, or really constrain it to the missions we looked at today?
Well, I can answer for SPG. I think the broader, well, I think first of all, from a pragmatic point of view, you want to start somewhere so that you get somewhere. And that might be 4 missions. But as I indicated in my presentation, and then Jeff emphasized, SBG would very quickly want to integrate international missions. And we're also very interested in integration with the NASA program of record, in particular, Glimmer and PACE.
I've got one more question. To what extent would you also use commercial data?
Kevin, that's a great question. And I think that that falls more in the space of the 200 algorithms that are the ambition of the community. So there's certainly a great deal of interest in downscaling from 30 meters to planet resolution for both thermal and VSWR products. In general, there's not been a lot of success in using planet to infill in the temporal domain, but that's getting better. And then finally, we have this walk-on objective associated with CO2 and methane point sources, where we would certainly see the opportunity to partner with GHGSat and Carbon Mapper as they come online. So yeah, the private sector from an SBG point of view, again, it's not the 10 core algorithms primarily, but the community definitely has articulated objectives and questions that would benefit from private sector data.
All right, thanks.
Just so we're clear, we've moved on into the open discussion section, so it isn't just for SPG folks here. Any further guidance for the SAWG? I don't know if I got a good clear answer on should we be constraining this architecture in this study to these 4 missions that we're looking at as a first order, or should we look at it in the larger sense that's being defined here?
Well, so I'll take that one. I think that you need to expand beyond the 4 missions somewhat, just in terms of, for instance, the discussion we just had, right? There's likely to be a need for products not only from NASA missions or data purchased by NASA, but also from, ESA, NOAA, USGS, and others that will really support the Earth system science kind of objective that you discussed. So, while this study, I would say 80% of it is really focused on the ESO missions and their processing environments and how we get open science to work within that. We simultaneously have to take, at least 20% of the effort and say, what external sources would really add significant value to helping better understand, the rest of the components, or augment or complement these ESO missions to help explain the rest of the components, including models. But we don't want you to try to solve everything either. So, I think about that percentage is right. About 80% or so of your effort should be just working with the group here, but being mindful of the full kind of capability that exists out there.
Okay, maybe one of the things we can do from what you just described there, Kevin, is maybe limit some of the use cases and how those other larger set of missions can be incorporated here, maybe thinking in terms of, just having data at the DAC and not necessarily interacting with them at the earlier phases when they're producing data, because obviously that could open up, a whole slew of missions.
But I think and Gerald just pointed this out in the chat. I think looking at some of the SNWG types of products as your use cases when you think about the architecture might be a good way to do it without having to do too much in terms of investigation on yourselves. Without too much additional work, I would say. So talking with the folks at JPL that are doing Opera or at Marshall or otherwise might be helpful in that context, because they're really trying to make multi-mission products.
Yep, that's a good point. I'm very familiar with that team. I think they're limiting their interactions to grabbing data from the DAC, which helps a lot. Okay, let's see. There was we addressed the cybersecurity concerns, timing. So that we're obviously seeing that the timing of these missions is a little bit different. NISAR is much later, in phase D, and they're getting closer to launch, where some of these other missions are very early in pre-phase A. How should we sort of take that scheduling mismatches into consideration? I mean, is this sort of the thought process to try and maybe focus on the ones that are a little bit more in development and think about those maybe places where if there is an architecture that is amenable to these things will be incorporated, and a mission that's a little bit later may have less of that opportunity to take that on? Any guidance for the SAWG in terms of considering that mismatch of schedule would be helpful.
I think in the NISAR instance, you saw their presentation. In a lot of ways, they're really close to this already. So I think it really kind of depends. However, for the remaining missions, we are still very, very early in everybody's planning phase. So what I would say is, historically, we probably haven't even had these types of discussions at this level of detail this early. And I might argue that, having a relatively good architecture by August next year isn't a high risk. I'm happy for people to push back on that. But, I think we've got, a number of years ahead of us where we typically would, improve the fidelity of the architectures for the mission processing systems. And I hope that this timing, we got started a little late on this, but isn't out of sync completely. So all that to say, if you have a really good argument why everything needs to be fully fleshed out, let's hear it. But if you can kind of go in with the basic assumptions that your responsibilities will likely remain similar to what they were before, but we need to make things a little bit open, or significantly more open, depending on who you are. That's a good basis to move forward with. I don't know if I answered your question there, Elias, but I don't think there's just a yes/no type of.
I think there's a general sense that you described there that we'll definitely take into consideration here. Let me turn it over to Wen-Ying. You had a question here as well?
Yeah, I have a question about the suborbital and in situ data. So I think many of the mission presented the, the validation plans using the in situ and suborbital measurements. I wonder what's the guideline that for the group in terms for those suborbital and in situ data in the OSS framework.
So the policies apply across the board. we've been over the past couple years really focusing on better support for suborbital activities. We have a group called the Airborne Data Management Group, which works very closely with campaigns as they prepare to fly in terms of developing data management plans, so on and so forth. And making sure that the information is cataloged and captured in a way that can be searched and discovered much better than it used to be able to do. So I would say that, you know, we will continue to work with them. The data is ultimately transitioned to a DAC. So presumably, if we select DACs earlier, you know, working with ADMG up front to figure out what you need to do with those campaigns will make it easier to move it into those DAC systems. The other thing is that increasingly we see people developing tool sets or services that make it much easier to integrate those suborbital or in situ based measurements. I think, you know, openness applies to that work too. One of the things we've done with our collaboration with ESA, for instance, is really incentivize the opening of ground data that previously was private, and making that available so that when people run their algorithms, they can, you know, in open platforms, they can verify the results using that higher quality data. So, you know, I think we have opportunities in that space too, right, in terms of those types of partnerships.
Were there any more questions from the SAWG members beyond the ones we just asked and looked at our document? Sounds like it's late in the day and our SAWG is SAWGed out like everybody else.
Yeah, we are several minutes over. Are there any last questions from anybody at all? I think, Kevin or any of the Andys, do you want to make any closing remarks?
I first want to thank you, Sarah, for doing a great job keeping us in line. And another thank you, especially to Elias, for running this exceptionally well and managing the SAWG, and as well as all the SAWG members for your participation, and also to the presenters. I know this was a very long 2 days, but we got a lot of great feedback and a lot of good discussions that were needed. Just taking some notes here, it seems like we may need another one to address some of these. So we're going to have updates. Please register if you haven't. That way we will be able to let you know when the recordings of this workshop are posted online, as well as the notes and responses to the Q&A. Andy, do you have anything else you'd like to supply, or Kevin? Or... We will be reaching out. Oh, sorry, Andy.
Yeah, sorry. I was just going to say thank you to everybody. I mean, it's been an incredibly rich meeting with some fantastic inputs, some fantastic conversations. So the SAWG is going to be a lot to do. So thank you, everyone.
Yeah. So we will be having follow-up meetings. I know in the beginning, Andy said there's going to be 2 other workshops, but just to let everyone know, you may be requested to be for some of your expert advice, so the SAWG may reach out to you on a one-on-one basis. But I know it's getting late in the day here on the East Coast, and I don't want to hold anyone else. Big thank you again. And thank you, Kevin.
Hey, I've just got to say, I know it's difficult to have these types of meetings, especially with all these, you know, conflicting and other meetings going on and being virtual. There's never a right time to do it. So we really do appreciate or never a perfect time to do it. So we really do appreciate your support and your attention to this, and really look forward to communicating about it quite a bit more over the next couple months. We'll make sure to have some sort of update every month or so, along with maybe an opportunity to field some questions as you have those.
Everyone have a good evening and a good afternoon for others, and sorry for keeping a little bit late.
Great job. Thank you.
Thanks, everyone.